Hey grade 12s, so in today's video we're going to check out math paper 2, the June 2024 Gauteng paper. I hope your exams are going well and let's jump right in. So question 1 here, so 1.1 says the data below shows the marks out of 100 obtained by 16 learners in a mathematics test, test 1. Okay, so here we have all of their numbers, all of the marks that they got, and 1.1.1 says calculate the mean mark for the test. So the mean is the average, so that means what we can do is we can add all of these numbers up and divide them by 16, or we can go ahead and use our calculator for the stats mode, because the next question is saying the standard deviation, so it means that we will need all of these values plugged into the calculator so that we can calculate the standard deviation. Cool. So we have our calculator here. What we're going to do is we're going to go mode. We're going to go number 3 over here for our stats mode, and then we're going to click number 1 because we only have one variable here. So once we plug in 1, we can go ahead and we can type in all of these values. So we're going to type in 67, then we're going to click equals, we're going to type in 77, click equals, 26 equals, and so on. Okay. Once we've reached all 16, we can just double check that there were 16 values as they said. So it means we typed in all of the values. And then from here, for the mean or the average for 2 marks, what we can do is we click AC. We then go shift, we then click 1 here for our stats mode, and then we go to number 4 for our variables. Once we click 4, we can go to number 2, the X with the little line above it is our mean. So we click 2, we click equals, and we have a value of 61,375. So we can just go ahead and write that to 2 decimal places. And with that, we just earned 2 marks. So stats is quite a nice section, provided we know how to use our calculator. It basically adds up to about 10% of the paper and is almost free marks, provided we know how to interpret it. What we want to do is work through these questions in this section relatively quickly so that we can save time for the later sections like Analytical, Euclidean, and Trig, and make sure that we get our marks at the same time. So 1.1.2 then says the standard deviation of the data. So good thing that we typed all of this in our calculator, because we can then click AC again just to clear the current information. We go shift, we then go stats again, we go 4 for our variables, and then what we're going to click this time is the 3. It looks like a little tadpole, a little O with a line here with the X over there. So we click 3, we click equals, and our standard deviation is 19,63. Cool. And with that, we just earned 1 mark over there, because the next question is requiring that we use both answers from 1.1.1 and 1.1.2 to calculate this, because it says the number of learners whose marks are outside one standard deviation of the mean. Okay, so what we're going to do is we're going to set this up. We're going to subtract this value from this value over here for one standard deviation lower than the mean, and then we're going to add this value to our mean over here so that we have one standard deviation above the mean. So let me just set that up and then we can explain that further. So what we're going to do is we're going to take our mean minus our standard deviation for the first lower rung over here, and then what we're going to do is we're going to add the standard deviation to our mean. So we can just go ahead, rewrite the values of both, and then solve for them in our calculator. So what we've done is we've subtracted our standard deviation from our mean and we've added it to our mean so that we now have a range here for our lower boundary and our upper boundary. What this means is that when we're going to reference the question again, it says the number of learners whose marks are outside one standard deviation of the mean. So that means we have a range with which we can look at these values here and see which of these values do not fall within this range, from the lowest being 41,75 to the highest being 81,01, which means we can just go ahead and count them. These aren't in ascending order, so we just have to look for them. This guy is below this value. This guy is below this value. This guy is above this value. This guy is above this value. So we have 4 so far. 83 is above 81,01 over there. And then 26 over here is also below it. So as we can see, every other value is within the range of one standard deviation on either side of our mean. Okay, our mean is our average. Our standard deviation is just the unit that we subtracted and added to our mean. It's like an increment based on this data, so that we can then interpret the data and figure out which values lie within this range and which values lie on either side of this range. So that means for our final answer, we can just go ahead and write down 6 learners, because 6 learners, as we checked off here, all fall outside of this one standard deviation range. So we write 6 learners, and that'll earn us 2 marks over there, because then from there, question 1.2 says the 16 learners referred to in question 1.1 above wrote a second test, test 2. The Box-and-Whisker diagram over here below shows the distribution of marks obtained by the 16 learners in the 2 tests. So test 1 over here was the previous set of data that they put, and then test 2 is now being mapped out so that we can compare it. Question 1.2.1 says describe the skewness of the marks for test 1. So if we're going to break down our box and whisker, what we have at the bottom is our min over here. This is the minimum value that the person got, and it corresponds at 26 over here with the 26 that we see over there. So as soon as we get to the box, we're dealing with Q1. It is the lower quartile. Over here, Q2, this is our median, the middle value of the whole data set. Q3 over here has to do with our upper quartile. And then over here, the maximum value, 94, is the highest mark that someone got in that test over there. So we have our max. This would usually be something along the lines of write the 5-number summary, or using this information to calculate the IQR, the Q3 minus Q1, the interquartile range. But at this stage, what we're doing is we're describing the skewness of the marks for test 1, for 1 mark. The way that we do that is we generally try and look at the shapes of how they are slanted. If something is more to the right, it is generally skewed left. If something is more to the left, it is generally skewed right. But the most accurate way to determine this is to write down our mean over here and compare it to our median. So if we're going to zoom in, we see that our mean is 61,38, correct, from the previous calculation. And if we're going to compare it to our Q2, which is 62 on the dot over there, we have our mean just to the left of our median. Cool. Which means that if our mean is to the left of our Q2, it means that we are skewed to the left. If our mean was to the right of our Q2, it means that we'd be skewed right. So it's all about the relationship between the mean and the Q2 to determine the skewness of our box and whisker, which means we can just go ahead and write skewed left, and that'll earn us 1 mark. And then question 1.2.2 says, which test was easier for the learners? Give a reason for your answer. Okay, so generally what we're going to compare is the middle value, because that gives us the most accurate data. For the whole box here, it represents 50% of the data. The line to the left is 25%, 25%. So it is split up 25%, 25%, 25%, and 25%. So that we have the whole split of the 100% of the sample size. But saying that, the maximum and the minimum are not good indicators. The range might be useful. Those guys are generally outliers, so they are less accurate to determine questions like this. Which test was easier? So which test was easier for the learners? Give a reason. What we're going to look at is the Q2 over here for test 2 and the Q2 over there for test 1. And what we can see is that Q2 for test 2 was 66 and Q2 for test 1 was 62, which means that the test that was easier would be the test that the middle value, or at least most of the people, got higher marks for. So that's what we're going to write. We're going to write test 2 was easier as Q2, our median, was 66, and in test 1 it was 62, which ultimately means that 50% of the learners got above 62 for test 1, but 50% of the learners got above 66 for test 2. And that means more people in test 2 got higher marks than test 1. And that just earned us 2 marks over there, which leaves us with the last question here, question 1.2.3. How many learners scored more than 84% in the second test? Okay, so 84%, this lines up over here. 84% is the end of our Q3 over here, which means that we have 25% of people in this range higher than 84%, okay? Which means that there were 16 people, 16 learners that wrote these tests. So all we have to do, it's asking how many learners scored more than 84% in the second test. What we have to do is go 25%, because this 25% represents this line portion over here, multiplied by 16, which is the amount of learners we have, and this will equal 4 learners. And that just earned us 2 marks over there, and a quick 10 marks for this whole section. Cool. So let's jump into question 2 here for stats, where we are going to continue with the June 2024 Gauteng paper. So 2.1 says, in a survey, a group of people were asked about the total distance that they had traveled from their homes in the last week of December 2023. The data collected is represented in the frequency table and Ogive over here, cumulative frequency curve below. So we have our frequency table and we have our Ogive or Ogive, however we say that. So these two guys are representations of each other. The frequency here is just the frequency on each rung, but the cumulative frequency is adding up each frequency as we progress, which means our cumulative frequency is 20 on this rung, but then 20 plus 30 makes this 50 over here. If we were to draw a separate column representing our cumulative frequency. Question 2.1.1 says, how many people participated in the survey? What we can do is we can potentially add all of these up, but right now we're missing the A and the B values, so we don't necessarily know it from this table. But what we can look at is the cumulative frequency. It means the collective frequency. And what we can do is we can go all the way to the last point over here, where we are seeing that the total value for everyone over here is sitting at 400. So we can just go ahead and write 400 people and we'll earn our 1 mark over there. And then 2.1.2 says determine the values of A and B in the table above. So what we can do here is we can map the information on the graph to the information from our table. One thing for Ogives is that when we're plotting it, if we were to do this in another test, we'd plot the anchor point, the lowest boundary point, at 0, just like they've done here. So 50 and 0 will be our first value. From there, as we plot it, we plot the upper point with the cumulative frequency, which means that here at 100, we plot 20. But as we go to 150 over there, which is the next upper point for our table range over here from 100 to 150, we have 50 for our cumulative frequency. And as we can see here at 150 kilometers, as they're represented here, the independent variable, we have 50 people for our cumulative frequency. So that is how we add this up, which means as we're looking here for 200, where we have our end point over there, 200, and we're trying to figure out A, what we have to do is we have to subtract the difference between the 100 and the 50, because what we had and what we can see is that we have 100 here for our cumulative frequency as we go to 200 for our anchor point over there, which means to increase from 50 to 100, we would have to have 50 over here for our value of A, because 50 plus 50 will give us 100 for our cumulative frequency that is plotted for the upper boundary anchor point of 200 over here. So that means for A, we can just go ahead and write 50. And then B, we're going to do the exact same thing. Over here, we're at 250. So that means we're here, 250. And we need to figure out how much was added from the previous point to make the cumulative frequency here 200, which means we were at 100. To get from 100 to 200, we'd have to add 100 over there. So that means our cumulative frequency will be 200 for that rung. And then we can go ahead and write the answer down that B is 100. So we could continue doing this for each rung, because as we can see for 300, we'd have 280, 200 plus 80 over there. Same thing again, 350 over here. For this rung would be 280 plus 70, we would be at 350. And then the last rung, 350 plus 50. So 400 is going to take us all the way up to 400. So we're plotting the cumulative frequency here with the lowest value at 0 and each upper value in each rung as the point we're plotting on the x-axis with the cumulative frequency on the y-axis. So we just determined the values of A and B in the table above and earned 2 marks, which means 2.1.3 over here says use the Ogive table to estimate the number of people who traveled between 100 kilometers and 300 kilometers. So between 100 kilometers and 300 kilometers. So what we can do if we're going to work from the table, at 100 we had 20 people, and at 300 we had 280 people as we established over here. So that means what we're trying to do is we're trying to figure out how many people traveled between this range. So all we need to do is subtract 20 from 280 and we'll have our answer. Okay, so we can go 280 minus 20 and that'll equal 260. So we just added all of them up and we saw that there were 260, and there is usually a leeway on the memo from 250 to 280 depending on how we subtract. If we were just making rounded estimates based on just looking at the cumulative frequency graph, the Ogive alone. So with that, we just earned 2 marks, and 2.1.4 says, if all people who traveled more than 350 kilometers were removed from the survey, how would this affect the median of the data? So if all people who traveled more than 350 kilometers, everyone over here was removed, how would this affect the median of the data? Okay, so the median right now, the median means the middle number. So as we're going this way, the median will be somewhere in the middle, for example. But if we are going to remove all of this, we have a shorter data set over here, and it means our middle is going to be a little bit more here because it is going to shift to the left or become smaller because we don't have all of this information at the top to estimate. It's like a midpoint. So right now the midpoint was over here when we had a longer line, but as we remove some of the line, the midpoint is going to move to the left as well, because then the middle point will be about here to there. So all we need to say here is that the median will decrease, and that just earned 1 mark over there. So question 2.2, the last question of this section, says if the estimated mean, the average of the data below is 16.4, so we have the average, what is the value of t? So right now we have our class interval 0 to 10, 10 to 20, 20 to 30, and 30 to 40. We have the frequency of each of these, and what we need to do to set up the mean for a table that has class intervals and frequency, we have to go 16,4 because that is our average, and then take the midpoint over here of this interval multiplied by the frequency. So that means the midpoint of 0 to 10 is 5. So we're going to go ahead, write 5 over there. We're going to multiply that by the frequency over here. So we're going to say multiplied by 13, and then repeat that with each row. because the next row is midpoint between 10 and 20 is 15. 15 multiplied by t is 15t. So we're going to go ahead, write 15t. Then again, midpoint of 20 and 30 is 25. 25 multiplied by 12 is the next value. And last row over here, midpoint of 30 and 40 is 35. 35 multiplied by 4 is what we're going to write down. So 35 multiplied by 4 is over there. So a reminder that mean is all the values added up divided by the amount of values in the data set. Okay, so what we're doing is we're taking the midpoint because we want the average multiplied by the amount of people that took this test, for example, or whatever we're measuring. And then what we have to do is that the average equals the total divided by the amount of people that we have. We have to then add up everything at the bottom. So 13 plus t plus 12 plus 4 is all going to go to the bottom. So we're going to rewrite that because then at this stage, we've set up our equation. So we have our mean equals the frequency times by the midpoint for each row over the frequency of everyone that we had in the sample size. So we can just go ahead, simplify our numbers. So 5 times 13 plus 25 times 12 plus 35 times 4 gives us 505 plus 15t, because we could not simplify that because it has a variable that we're trying to solve. So we have that over there. And then at the bottom, 13 plus 12 plus 4 is 29 plus t, because we could also not simplify the t over there. So this still equals 16, 4 over here. And then what we have to do is we have to take our 29 plus t up here and multiply it by the 16, 4. So 16, 4 multiplied by 29 is 475,6 plus 16, 4 multiplied by t is 16, 4 t. And that still equals 505 plus 15t. And then we can take this 15t over to this side. So we can go 16, 4t minus 15t, and we have 1, 4t. And then 505 minus 475,6 is 29.4. So last thing, taking this 1, 4 over. So we're going to go 29, 4 divided by 1, 4. And our final answer for t is 21. Okay. And with that, we just solved the value of t, just like we would an algebraic equation, but in the context of stats using this formula. Okay. So that just earned us 4 marks over there and 10 marks for this whole section. So what we're going to do now is work through question 3 here of the June 2024 Gauteng paper for math paper 2. And we're going to start with the analytical geometry. So question 3 says, in the diagram below, the equation of line AD, so AD over here, is 2y plus x equals 11. So we have 2y plus x equals 11. M is 1 and -1 is the midpoint, so that's important, of the straight line joining B over here and C over here. The angles of inclination of AD and BC, so AD over here and BC over here, are alpha and beta respectively. So we have E over here and F over here are the y-intercepts, also important, of AD and BC respectively. So we have our formulas up here. We have our distance formula, our midpoint formula, our straight line equations, these two options over here, our gradient formula, our equation of a circle formula for question 4, and then our m equals tan theta for any angles of inclination. So question 3.1 says, determine the coordinates of B, so the A and the B over here, both of these unknown x and y coordinates. So what we have to do for 3 marks means we're going to use the midpoint formula here on line CB, because they told us the coordinate pair of m, which is 1 and -1. Okay, so what we can do is we can set up an equation for each of them. So we have our x of m equals x1 plus x2 over 2. And then we have our other side of the equation. We have y of m. M is just the midpoint over here, is y1 plus y2 divided by 2. So that means x of m, the x value for m is 1 over here, the x value for our c is 3 over there, and then x2 is our a value over here. So I'm just going to plug in a over there, and then this is divided by 2. So we can go ahead and solve for this. So multiply the 2 up there. So we have 2, and then take the 3 over, minus 3 equals a. So our a value is minus 1 over here, and we can see that it is on the left side of our y-axis, which means a negative value is correct. It's just a way to verify that our calculation lines up with the way that it is plotted, which means we can do the same for ym. Our y value for m is -1, and this equals y1, which is 4 over there, plus y2, which is our b value over here, and then divided by 2. So we're going to solve it the same way, multiply the 2 up, which is -2, and then take the 4 over, it becomes a -4. So this equals b, and our b value is -6. So right now, the coordinates of B are -1 and -6. And that just earned us 3 marks. So from there, we have question 3.2, which says determine the gradient of BC. So BC is this line over here, and we have just calculated this point B over here. But if we take B or M or C for the gradient formula, it will all be correct because they are on the same straight line. So the gradient formula, as we can see here, is our M is y2 minus y1 over x2 minus x1. So we can just go ahead, write that down. So we have our formula over here. So our y2, I'm just going to use the points C and M over here. So we have 4 minus -1, so that becomes +1. 4 minus -1 is +1, and then that is over the 3 minus 1 over there for the x values. So we can go ahead, plug this in our calculator, and we have 5 over 2, and that'll be our final answer. So 5 over 2 is the gradient over here, and that just earned us 2 marks. And then from there, we have question 3.3, which says determine the size of theta correct to 1 decimal place. So as we can see, theta is over here, and what we need to do is we need to get this angle alpha over here, this angle beta over here, so that we can then do exterior angle of a triangle, because this angle plus this angle equals this angle over here. And the way that we do that whenever we're trying to get sizes of angles is m equals tan theta. So I'm going to go ahead and write that over here. So instead of theta, I'm just going to write alpha for this guy, just because we're going to get alpha first. So that means we need the gradient of this graph, and the way that we're going to get the gradient is by manipulating this formula over here. Because what we can do is we can try and get this into standard form, and then we can get our gradient from our standard form, which is y equals mx plus c. So the m over here, once we manipulate this so that y is by itself with no numbers in front, will be our gradient. Okay, so what we can do is we can take this x over, so it becomes 2y equals minus x plus 11. Off the bat, I just put the x first just so that it is in the standard position, and then from there divide by 2, so we have y equals minus 1 over 2x plus 11 over 2. From there, as we mentioned, this is our m value, -1 over 2, so we can go ahead and plug this in over here, make this equal tan of alpha, and this will give us -26,56. Okay, so alpha's value is not that yet, because what has happened is we have a decreasing line. So the negative gradient means we're going to unwrap it this way. So what we have is this value over here, so we're just going to have to add 180 to get to this value over here. Okay, because once we add 180, we're doing angles on a straight line. This -26,56 plus 180 will give us the alpha over there, and our value for alpha is 153,43 degrees. So now that we have this angle over here, all we need to calculate is beta over there, and we're going to do the same thing over there, because in 1.3.2 we determined the gradient of BC. So if we're going to calculate this, we're going to say m equals tan beta. Tan beta over there, the gradient that we calculated in 1.3.2 was 5 over 2 over here. So we write that. We're going to use our calculator, divide by tan, just as we did the previous one. So we go shift tan 5 over 2, and this gives us 68,198. So we have 68,198 over there for our degrees. And because this was a positive value for tan, it is going to unwrap this way, anti-clockwise, and reach there. It doesn't unwrap clockwise like a negative gradient does. Okay, so it unwraps like there, and we have beta just like that. No need to add 180 or anything like that, like we did for the alpha over here. So at this stage, all we need to do is say theta plus beta equals alpha, because exterior angle of a triangle, and then we'll have our answer. For this section, analytical, we don't have to use any reasons, so that's cool over there, which means that theta plus beta equals alpha. Alpha, as we established, was 153,43. Beta, if we're going to take it over and subtract it, is 68,198, and that leaves theta by itself with a final answer of 85,2 degrees, because we had to round this to 1 decimal place, so we just had to round it to a 2 over here. Okay, and with that, we just determined the size of theta correct to 1 decimal place for 4 marks. And then question 3.4 says determine the equation of line BC. So BC is this line over here, and we want the equation in the form of y equals mx plus c. So line BC, we already have the gradient of it as we established from question 3.2. So we have a 5 over 2 over here for the gradient. The x is what we're going to plug in, and the y as well, so that we can solve the c value. Because once we have the c value, the y-intercept over there, we'll then have our full equation. So all we need to do is find a point on line BC to plug into this equation, the x and the y coordinate, and then we can solve for c. So what we can do is plug in this value here for m. The y value is -1. 5 over 2 is there. The x value is 1, so that's not going to change anything. And then c is here, which means 5 over 2 times 1 is just 5 over 2, which means if we take it over, it's -1 minus 5 over 2, which if we plug in our calculator is -7 over 2, and that is the value of c, which means for 2 marks, we just need to rewrite it in its standard form. So we have y equals 5 over 2x minus 7 over 2. Cool. And that just earned us 2 marks to determine the equation of line BC. And then last question here, 3.5 says determine the area triangle CEF for 4 marks. So triangle CEF is over here. We have CEF over here, and we need to determine the area of it. Okay, so there will be 2 options. We can either use the trig and triangles formula, or we can use half base times perpendicular height. So the easiest way that I can see for this option is to go half base, which is our EF over here, times perpendicular height, which is the value from there all the way up to here. So perpendicular height requires a 90, and that's going from the base all the way to the highest peak, which is over here at coordinate C, 3 and 4. Okay, so in order to get the length of EF, we already just calculated the equation of line BC. We know the y-intercept is -7 over 2, so -7 over 2 is the y-intercept over here. And then the y-intercept over here for E is what we calculated earlier for the straight line equation when we got this guy into our standard form, because plus 11 over 2 is the value here for E. So all we need to do is add 11 over 2 plus 7 over 2 to walk all the way from E to F. So we're just adding them up to get the distance here. We don't have to use the distance formula because they are on the same vertical plane. There's no change. They aren't diagonal like this guy, which means that 11 over 2 plus 7 over 2 gives us 9 units there for the length of EF. And then what's quite nice is that we're on the y-axis over here, which means for the perpendicular height, all we have to do is move horizontally 3 units to get to point C, and that'll be the height over there, because we're going from 0 all the way to 3 in terms of x for C to get the perpendicular height, which means the length from y-axis to C is 3 units as well. So we have our base, we have our perpendicular height. We can just go ahead and plug that in the formula. So we have half base, which is EF, which is 9 units, multiplied by perpendicular height, which is the y-axis here, all the way to C, and that is 3 units. So that means 9 times 3 is 27. Half of that is 13.5, and our final answer is 13.5 units squared. And that just earned us 4 marks over there for question 3.5 and 15 marks for this whole section. So we're going to check out question 4 here, which is analytical geometry or circle analytical geometry. So it says the diagram below shows a circle with center P over here and an equation of x squared plus y squared minus 6x minus 4y equals 12. It says the circle cuts the y-axis over here at point R and S. RT over here is a tangent to the circle at R and cuts the x-axis at T. Angle theta is indicated. So then it says 4.1, determine the coordinates of P as well as the radius of the circle. So the easiest way to do that is to reference this equation that we have up here, where we have the equation of a circle, x minus a squared plus y minus b squared equals r squared. They've given us a lot of information over here in terms of the x squared plus the y squared minus 6x minus 4y equals 12. What we can do is manipulate and rearrange this formula and get it in our standard form here to figure out the a and the b, which are ultimately the x and the y coordinate for our p over here, and the r squared, which is the radius. So I'm going to go ahead and rewrite this equation that's been given to us with the x values next to each other and the y values next to each other. The reason I left a little bit of space is because we are going to have to complete the square for this one, and whatever we do to this one, we have to add on this side. Whatever we do to this one, we have to add on this side as well. Which means that in order to complete the square for an x squared minus 6, we're going to have to divide this guy by 2 and then square it. So if we're going to go minus 6 divided by 2, that becomes 3, and then we're going to have to square it over here, which makes this value here positive 9. So we're going to have this, we're going to put brackets here because we're going to try and convert this into the x minus a squared portion over here. We're going to do the same thing here for y squared minus 4y. So what we have to do is we have to take minus 4 divided by 2 and then square it, which becomes 2 squared. And 2 squared is 4. When we square it, the negative is going to disappear on both of them, and that's why they become positive. And here we have our plus 4 over there, and all we need to do is we have to add the positive 9 and positive 4 on this side, because what we do to one side, we have to do to the other side so that it does not change its meaning, and that the left side still equals the right side. So from here, it's quite nice, because all we have to do is we have to turn it into like brackets, which means we have an x over here, we have our y over here, and these guys are perfect squares, which means that a minus 3 times a minus 3 will give us the positive 9 over here. So if we're going to do our SMS method just to double check the sign, we have x times x is x squared, x times negative 3 is minus 3x, times 2 is negative 6x, and then minus 3 times minus 3 is positive 9 over there, which means that we are correct here. This bracket has the same meaning as this bracket over here. So then we're going to do the same thing here. We have plus, and then we're going to say minus 2, because y times y is y squared, y times minus 2 is minus 2 times 2 is minus 4y over here, and then minus 2 times minus 2 is positive 4 over there. And then, as we can see, this guy is shifted to the right and shifted up, which means a minus 3 will shift us 3 units to the right, and a minus 2 will shift us 2 units up over here for our p-value, which means that it is fitting the correct quadrant as well, as far as location, that this is a minus and a minus. And then we can just add this up. 12 plus 9 is 21, 21 plus 4 is 25 over there, which means if we're going to get this in standard form, we already have the left side over here, which is x minus 3 squared plus y minus 2 squared, and then we're just trying to link it back to our r squared over here, and that means we're going to take a square root of 25, and the square root of 25 is 5, because 5 squared still equals 25, and that gives us the standard form here of x minus a squared plus y minus b squared equals r squared, which means the coordinates of p, as we mentioned, are 3 for the x value and 2 for the y value over here. And then the radius, as we established, is 5 over here as well. And that just earned us 4 marks over there. Then from there, we have question 4.2. It says, show that the coordinates of r over here is r, 0, and 6. So what we can do is we can then use our equation here. If we couldn't solve the equation, we could use this unsolved equation here and still solve it the same way. Because what we know about point r and point s as well is that the x value is 0. So that means we can just rewrite this equation down and plug in a 0 where our x value used to be. Rewrite this, and we're going to try and solve for the y value because we want the y value over here. So at this stage, we plugged in 0 over here. We made the 5 squared equals 25 again, just because we're going to try and solve for everything. So 0 minus 3 is minus 3, and minus 3 squared is 9. So we don't have to FOIL this guy. 0 minus 3 are just numbers, and we can just simplify them in our calculator, and minus 3 squared is just 9 over there. Then we're going to do the SMS method for our brackets here, y minus 2. So y times y is y squared, y times negative 2 is minus 2y, multiplied by 2 is minus 4y, and then minus 2 times minus 2 is positive 4. Okay, and this all equals 25, which was the 5 squared. From there, we can take everything over to this side where our y squared is positive. So we have y squared, nothing to simplify there, minus 4y, nothing to simplify there. And then 9 plus 4 is 13 over there, minus 25 is minus 12, and that equals 0. From there, we have a quadratic equation, because that means we're going to get 2 different values for y, which makes sense because one of the values is going to be the y-intercept of r, and the other value is going to be the y value or y-intercept of s. So we can go ahead, open up our 2 brackets. We have y in one bracket, y in the other bracket, just splitting up our y into both brackets. That equals 0. And then the factors of 12 are 1 and 12, 2 and 6, and 3 and 4. Okay, which means which 2 of these factor pairs can give us 4? It looks like 2 and 6 would be the the best option. So we're going to write 6 and 2 over here, because 6 minus 2 will give us a negative 4 over here. So that means to get a negative 4, the bigger value has to be negative. So the 6 has to be negative, and then this value is going to have to be positive. Also because a negative 6 times a positive 2 will give us the negative 12 over here, which means that the two different y values, y equals 6 or y equals minus 2. And if we're going to interpret the graph over here, minus 2 we can see will be the s value here because it is negative, and r is going to be the 6 because the y is 6 for the r value. That means show that the coordinates of r are 0 and 6, or is 0 and 6. We're therefore going to write r is 0 and 6, and that would earn us 2 marks over there. And if we were unable to solve r, we would just use this value that was given in the next question, because they usually give a question like this in order to use this answer in the next question. And then 4.3 says determine the equation of tangent RT in the form of y equals mx plus c. So we have a straight line, that is our tangent. Tangent means that we only touch the circle once. And what we already know now is the value r over here is 0 and 6, which means that this is our c value, 6 over here, because that is the y-intercept where x is 0, the y value is 6, which means we just need to calculate the m value, and we therefore need one coordinate point to plug in to the x and the y. But we don't have a coordinate point on here, so when we have tangents, we have to remember that there are some rules from Euclidean that can help us, like tan perp rad, because what we have is the point r, and we have the point p that we calculated earlier, which means we can get the gradient here. This gradient multiplied by this gradient will equal -1, because they are perpendicular, because we established that tan perp rad makes a 90 over here. So what we are going to do is we're going to take the gradient of rp, and our r value, the gradient is m, our y value for r is 6, minus the y value for p is +2 that we have over here. The x value for r is 0, minus the x value for p is 3. So what we have is 6 minus 2 is 4, 4 over minus 3 is -4 over 3. And now that we have the gradient of a decreasing line from r to p, we can multiply m1 by m2, and this equals -1 because of tan perp radius. We don't have to write down the reasons. We don't get any marks for reasons unless they specifically ask us. But then that means we can write -4 over 3 here for the gradient of rp, our m1. m2 is what we want. That is the gradient of tr over there. And this equals -1. So we're going to divide -1 divided by -4 over 3. And what we have is this value is always inverted and positive. So that'll give us a value for m2 as 3 over 4 if we plug that in our calculator, which means we just solve the value of m2, the gradient of tr, and we can just go ahead, plug that in. So we have y equals 3 over 4 x plus 6. And that just earned us 3 marks over there, determining the equation of tangent RT in the form of y equals mx plus c. Because then from there we have question 4.4, which says determine the size of theta over here correct to 1 decimal place. Just like question 3, correct to 1 decimal place is usually what they want for any angle questions in analytical. Okay, but just follow whatever instructions they give us. So the easiest way to get theta over here is to use the information that we calculated in 4.3, because they usually make us calculate a question to use that answer in the next question and so forth, which means that in order to get theta over here, we can do exterior angle of a triangle, because here we have a 90. Here we can calculate this angle of inclination here because we just calculated the gradient here for this tangent TR. And what we know about exterior angles of a triangle is that this angle theta over here will equal the angle of T plus the angle of O over there, because this angle on a straight line, this plus this equals 180, and this plus this equals 180. T plus 0 plus R, the inside portion of the triangle, equal 180, which means we can just do exterior angle of a triangle, and then we can solve for theta like that, which means O, or TOR, we already know is 90 because it is on our Cartesian plane. It is where the X and the Y line meet, and it is 90 perpendicular to each other. Okay, which means what we have to do is use our M equals tan theta formula again, just like question 3, and we're gonna plug in the M, the gradient of our line TR, our tangent TR over here, which we calculated in the previous question as 3 over 4. 3 over 4 equals tan theta. If we're going to use our calculator and go shift tan 3 over 4, we have the value of 36,87. So we can go ahead and write that down. 36,87 degrees is the value of OTR over there. So OTR is the angle over here, which means that theta is just 90 plus angle OTR, and therefore theta equals 90 plus 36,87, and that equals 126,9 degrees. A reminder that we're rounding to 1 decimal, so we round it up to 1 decimal as 9 degrees over here. And that just earned us 3 marks over there. Because then from there we have question 4.5, which says a vertical line is drawn as a tangent to circle P at Q, A, B, where A is greater than 0. Okay, so that means the x value is positive. Write down the coordinates of Q. So a vertical line is a line that is going perfectly up, and that means the only 2 options would be here if that was touching once, and here if that was touching once. But what we know based on this restriction is that it's where A is greater than 0, where A is positive. So that means it is exactly here. A is positive because the x value is positive on this side of the circle. It is not positive on this side of the circle. Okay, so we've established it's a vertical line, it's on this side of the circle, and it's a tangent, so it's only touching once. Saying write down the coordinates of Q. So what we know is our P value here is 3 and 2. So we have our P here, it is a 3 and a 2 over there. That's the coordinate pair. So in order to get the coordinate pair that is as far to the right as possible, just interacting or touching this tangent once, what we can do is we can add the length of the radius that we established here as well. So here was our radius from question 4.1, and here was the coordinate pair of point P from question 4.1 as well, which means that if we know that this is 3 and 2, all we have to do is add 5 units to the x value. Because what we're going to do is we're going to move perfectly horizontally. We're going to add 5 units to our 3 here without moving up or down at all, which means our y value is going to be the same and our x value is going to be 3 plus 5. So our q over here is going to be 8 and 2 because we moved 5 units because of the length of the radius, adding 5 to our x value of our p, and we did not have to do any shifting up or down for our y value over there, which means q is 8 and 2 over here, and that's why we only had to write it down. There was no calculating, it was just using previous information to write down our answer based off of interpretation, and that just earned us 2 marks over there. Okay, and now 4.6 says for 4 marks, for which values of k will y equals positive 3 over 4 x plus k be a secant, or secant, I don't know how we say that, to the circle. So what we have is a line y equals 3 over 4x plus k. K means we are going to affect our c, our y-intercept, by shifting a graph up and down. The fact that this is 3 over 4 is similar or exactly the same as the gradient of our tangent. So what we know here is that this tangent here is y equals 3 over 4x plus 6. So they're saying for which values of k will this thing be a secant to the circle. A secant is a line that touches a circle twice. So right now this tangent only touches it once. But if we were to shift it down a little bit, if it was exactly parallel, it would be touching here once and here once. So a secant goes through a circle twice. And what they're asking us is to find which value of k, the y-intercept, will make this statement true. Because right now we know that k, when it is less than 6, it will start to cross through twice. Because when the k, which is our y-intercept value here, is 6, it is exactly equal to it once. So say now we make it a little bit smaller. Say now we make it -5. Then we're going to shift this exact same line down a little bit so that it's intercepting with +5 over here. So we've shifted it down 1 unit, it is +5, and now it is crossing through once and twice. So we can keep doing this. Say now we make it 2 over here, just like it is in line with this line. We're going to draw a line through here, and as we can see, it is still a secant. It is crossing through once and twice over there. What this means is that it's going to be any value that is less than 6, because 6 right now is telling us that we're touching it once. But if we keep moving, say now we're moving here, it is still touching there twice and twice. Say now we have a -3, for example, is the y value. That is still true, but there will come a stage where we are going to shift this same line down to a point where it is only touching once. Just imagine that this thing is touching just once, and then that'll be a tangent 2. And then as soon as we're past this range, for the y-intercept over here, from 6 all the way down to, let's hypothetically say this is minus 9. As soon as we're lower than minus 9, this graph is going to be not touching at all and no longer a tangent. Okay, so what we're seeing is we have this line with this gradient just like we have our tangent here, and we can move it within a very narrow range in order for this statement to be true that it is a secant, that it is crossing through twice. So that means right now we know this point R, but what we have to do is we have to get the point that is directly opposite it, because we know the y-intercept value here. We know that it is less than 6, but we don't know what it has to be greater than. We don't know if it's -9 or -8 or -7 or what. So that means what we can do is we can do a midpoint formula backwards to figure out the point over here that this tangent is touching as well, only once. Because then, once we're there, we can establish the lower boundary of our range, okay? We could always do roots, but we aren't going to explain that in this video because then we're going to make them equal each other, get k into our roots formula, and then solve for it from there. But it's much easier if we're just going to do our midpoint working backwards because we know R and we know P. So we can figure out this point, this coordinate over here, and then work from there. So that means if we're going to do midpoint working backwards, we have the x value of 3, we have the x value of 0 over here, plus the x value of what we want over there. So we're just going to call that x2, and that is over 2. So 2 times 3 is 6, plus 0 has no effect, so therefore the x value here is 6. From there, we're going to do the same for the y value. So 2 is the y value over here for P, the midpoint. And we're going to say R is 6 over there plus y2 equals 2. And then therefore 2 times 2 is 4. 4 minus 6 is minus 2. And y2 is -2 over here. And this corresponds because we have a y value that is below the x-axis, which means that we can go ahead and we can try and calculate the c value, the c-intercept over here. So we have the x and the y value on this line. We know that the gradient is the same, so we can just go ahead and rewrite this. We have y equals positive 3 over 4x plus k, and then the x value is 6, 3 over 4 multiplied by 6 plus k over there. Y is -2. 3 over 4 times by 6 is 9 over 2, and then we're going to take that over. So -2 minus 9 over 2 equals -13 over 2. So what we've just done is midpoint formula backwards to figure out this coordinate here, and then we just plug this coordinate pair, 6 and -2, into the same equation with the same gradient in order to calculate the c value over here. So the c value is the y-intercept, and that is what k represents, which means that k, being -13 over 2, will be exactly the y-intercept where this line touches the circle just once and is a tangent, which means we can write this as the lower boundary over here because we have just completed this answer for 4 marks. And what we're saying is that this k value, this y-intercept, has to be any value greater than -13 over 2, which means it can be here because as soon as we're here, we're cutting through the circle twice, and it can be any value going up and up and up until it is less than 6, because over here, before 6, it is also cutting twice. Exactly at positive 6 and exactly at -13 over 2, the y-intercept shift makes this line a tangent to the circle. So when our equation is y equals 3 over 4x minus 13 over 2, we have a tangent over here touching the circle once. When we have the same equation, y equals 3 over 4x, but plus this time positive 6, we have a tangent touching the circle just once above it, which means that in order for it to be a secant, the y-intercept can be any value greater than -13 over 2 to any value less than -6, because then we have a line cutting through there twice, through there twice, through there twice, and so on. So let me know if that makes sense, or if there are any questions in the comments below on that one. But whenever we see k, we are trying to see how we can shift the y-intercept to make whatever statement they have true. Sometimes they could be asking about a tangent, other times a secant like they have here, sometimes not intersecting at all. And we just have to interpret how we can shift the line based off of the y-intercept being the value here that they usually put as k. So that just earned us 4 marks over there. And then last question here, 4.7, for 4 marks, it says another circle M with the equation x plus 3 squared. So x plus 3 squared plus y plus 2 squared equals 36. Okay, so it's a little bit different from this graph. We initially had -3 and -2, and then 5 squared, which becomes 25. So that means we have x plus 3 squared plus y plus 2 squared equals 36 or 6 squared. So we have a new circle over here. They're asking, will circle M, this new circle, touch or cut circle P, or will it neither touch nor cut circle P? Show all calculations to determine your answer for 4 marks. So off the bat, before we learn the formula, we're just going to try and draw a rough sketch just to see how we think this might work. Because a +3 is going to move us -3 units this way, and then a +2 is going to move us -2 units down here. So what we have is a point that is directly opposite in this third quadrant over here, 1, 2, 3, and what we have is the radius is 6 units. So if we were to draw this, the circle is going to be a little bit bigger, and then it's going to go something like this. So just off the bat, this is telling me that this is very likely to touch twice, just by doing a rough sketch, knowing how we've shifted the x and the y value and made the radius a little bit bigger. So that being said, the first thing we have to do for a question like this is do a distance formula between the centers, because we have our center over here. We know that it is -3 and -2. So if we do a distance formula here, we can then interpret it. Okay, so our distance formula is d equals square root x2 minus x1 in brackets squared plus brackets again y2 minus y1 squared. So we can just go ahead and rewrite that and plug in our values, because x2 minus x1, we have 3 minus -3. So 3 is the x value here for the initial circle. The other circle is -3 there, but our formula is saying minus. So it's minus minus, which is a plus 3 over there. That is squared, plus the y value here is 2. Once again, minus -2 is +2. So we have 2 plus 2 over there. That is squared as well. So if we go ahead and plug this in our calculator, we have 2 third 13, and that will equal 7,21. But right now, we have a formula that we can use to determine whether this is going to cut through twice. Because what we're going to do is we're going to set this up. We're going to go capital R minus small r is less than MP, or MP is greater than it. And then this is less than R plus R. So our R plus R is greater than our MP over there. Okay, so what this formula means is that this is the radius of the bigger circle. So that just means it'll be our second circle here. So we're going to go 6 over here, and then the radius over here, because they told us that it is 36 here. So we have our radius, which is 6 squared. So we have 6 over there minus small r is the radius of the previous circle. And we established that that was 5. So we go 6 minus 5 over there, and that is going to be less than MP, which is our gradient over here, which is the distance we calculated between the two centers. MP is the P over there, M is this midpoint of this circle over here, and we have 7,21. And then what we're going to do is we're going to add them up. So R again, as we established, capital R was 6 and small r was 5. So we're just adding them up. What we're trying to do is see whether the distance of the line M to P is in between this range, this lower boundary of capital R minus small r, and this upper boundary of capital R plus small r. Because what we have is 6 minus 5, that is 1. 7,21 is in fact greater than that, and it is in fact less than 11, which is 6 plus 5. Because what we're saying by putting the distance of MP in between the lower range and the upper range, we're saying that it is touching twice. Okay, so I'm just going to write that conclusion down first before we explain the other scenarios. Therefore, for 1 mark, circles will cut twice, because the distance of MP from here to here is in between this radius over here minus this radius over here. So we're saying that the distance from there to there is greater than this radius over there minus that radius over here. And then what we're saying for the upper portion is that this radius over here plus this radius over here, the distance from here to here is also less than their collective radii. If this radius plus this radius was less than the distance between them, then these circles would not be touching. Okay, so we've solved this. We have the distance of MP, and it's in between the radius of the bigger circle minus the radius of the smaller circle, and it is greater than that, but it is also less than the radius of the bigger circle plus the radius of the smaller circle. So that is our proof that our circles will cut twice, but we're going to run through the different scenarios. So right now, say now we have a circle here and a circle here. If we have this circle here and this circle here, and we calculate the distance from here to here, so this is our distance. it will be greater than this radius over here plus this radius over here. Because here's our small r, here's our capital R. As we can see, the distance is greater than those two radii added together. So that means this sort of scenario will show us that these circles are not touching. If our distance between the centers is greater than this radius plus this radius. But say now we move this circle a little bit closer and it's touching once. That means the distance from here to here, so distance from midpoint of the circle to midpoint is our D, will be exactly equal this radius plus this radius over here. So R plus R means that they'll be intersecting just once, but they will be outside of each other, okay? The circle will not be inside the other circle, because then the next situation is what we're dealing with right now, is we're saying that the distance from here to here is in between this radius minus this radius. So the distance is in between this radius minus this radius and this radius plus this radius. It is just the setup to know that we are intersecting twice over here, when our distance is in between the one radius minus the other radius and this radius plus that radius. Okay, it's just telling us the range over here that they're intersecting twice, because then two more scenarios, we have a circle inside another circle. So we have our distance from here to here, and our distance is equal to this radius over here minus this radius over here. So we're going to say R minus R over there, because that will be the same distance from the midpoint to the midpoint over there. And the very last scenario is if there's a circle inside the other circle and they are not touching, we have our distance from here to here for the midpoint of the big circle and the midpoint of the smaller circle, and the distance will be less than this whole radius here minus this whole radius here. The radius of the big circle minus the radius of the smaller circle. The distance will be less than that, which means that they are not touching at all. Okay, cool. And those are the 5 different scenarios based on how we interpret the distance between the midpoints of two circles. But in this scenario, as we could see, the distance was between the big radius minus the small radius and the big radius plus the small radius. So therefore, we know that the circle will be cutting twice. And with that, we just earned 4 marks and 22 marks for this whole section. So what we have here are our double angle rules over here and our compound angle rules over here for when they come up during this section. So question 5.1 says, simplify the following expression without using a calculator. So we have tan negative x times sine 90 plus x plus sine 2x over 2 cos 360 degrees plus x. So 6 marks. I'm just going to rewrite this for us and then we can get going. So what we're going to do is work through each trig function one by one. So we're going to start with the tan negative x over here. So what we have is our cast diagram, which is always important if ever we're going to do reductions like this, because we have 0, 90, 180, and 270. A reminder that what our cast diagram is telling us is that cos is positive here, all of them are positive here, sine is positive here, and tan is positive here. So if we're going to place tan negative x, what it is saying is that we have 0 degrees minus x over here, which means 0 degrees minus x is going to place us in the C quadrant over here, where cos is positive, which means that tan is negative, and we can take the negative out and place our angle x over here. From there, we have the sine 90 plus x. This is a cofunction. So whenever we see 90, we have to think cofunctions, and cofunctions have to do with sine turning to cos and cos turning back into sine. And what's happening, if sine is 90 plus x over here, sine is already positive in this quadrant, which means we're going to take the positive out and then turn this into cos of x. So all we do is we take the sine, positive or negative, based on the quadrant that it is in, and then we change it from sine to cos or cos to sine if it was vice versa. So we've just placed this guy over there, and then what we have here is sine 2x. So the thing with sine 2x is whenever we have a 2 affecting the angle itself, it means it's a double angle that we need to expand, because we usually can't cancel any trig function when there is a value affecting the angle, which means sine 2x or 2 theta is quite nice because it can only expand into one variation over here compared to cos 2 theta, which can expand into 3 different variations, as we can see, which means I'm just going to go ahead, expand sine 2x into 2 sine x cos x. And then we have that over 2 cos. I'm just going to leave that there for now. And then 360 plus x, if we're going to look here at our cast diagram, this guy is 0, but it is also 360 degrees, because what's happening is that we unwrap anti-clockwise like that, which means we go from 0 to 360, then we can add again to 720 and so forth, which means that if we're going to go 360 plus x, it's going to place us in the all quadrant over here where cos is positive. So we can just drop the 360 and place our x over there, which means we've dealt with this guy over here, we've dealt with the denominator as well, and now we can see what the next move is on this line. Because usually when it comes to tan, a good thing to do is expand our tan into sine over cos. So I'm just going to leave the negative out here, expand the tan into sine x over cos x, and then a reminder that this is multiplying this positive cos x over here. And I'm just going to place this cos x over 1 so that we can see that we can cross cancel the cos x and the cos x over here, because that's usually what happens with the tan x, is that we expand it so that something can cancel. So over here, I'm just going to rewrite this whole fraction for us. And now we can go ahead and start canceling some stuff, because as we mentioned, this cos x can cancel with this cos x. This negative sine x will remain. 1 over here will also remain. And then what we have on this side of our plus, because we can never cancel cross any pluses, only if things are directly multiplying each other, is we can cancel this cos x over here and this cos x over here and this 2 over here and this 2 over there, which means all that remains is a negative sine x from this left side of our plus sign and a positive sine x on the right side of our plus sign, which means negative sine x plus sine x is 0 over there, and that is our final answer for 6 marks. So the best thing to do for 5.1 is to draw our cast diagram so that we could place any of them and then expand any double angles or compound angles so that we can simplify accordingly. But that just earned us 6 marks over there. And now 5.2 says, given that sine 27 equals p, determine without the use of a calculator each of the following in terms of p. Okay, so we're not trying to solve for p, but we are going to have to do a construction over here, because what's happening is we have sine 27 equals p over 1. And we see that they say without the use of a calculator, and that's a clue that we have to do a construction. So we have different types of construction questions in trig. One of them has to do with our Cartesian plane, but this one just has to do with drawing a triangle in the first quadrant. No need to place it in any quadrants. So we have a right angle triangle over here. What we have is 27 over here as our reference angle, and then we're dealing with sine. A reminder that we have SOHCAHTOA, which is sine equals opposite over hypotenuse, cos equals adjacent over hypotenuse, and tan equals opposite over adjacent, which means that we've started with sine 27 here, which means we have p over 1, and this is telling us that our opposite is p over here. So the side opposite our reference angle is p, and our hypotenuse is 1 over there, which means we can just go ahead and do Pythag to get this side over here, our adjacent, which means we have 1 squared equals p squared, plus we'll call it x squared, which means if we take this over, 1 squared is just 1 minus p squared over there, and then we take the square root of that, and that'll equal x over here, which means this value over here is just 1 minus p squared. And this is good for us because we have almost all the information to do with this triangle, 3 sides over here and 2 angles, and all we need to get is just this angle over here as well. So if we put that in our calculator, we have 180 minus 90 minus 27, and we have 63 degrees, which is an important thing because we're going to see that we have 63 degrees here for 5.2.2, and we might wonder where that angle came from. We can always do a co-function to see that, but if we just place all the angles from the get-go, it'll help us a lot. Because now that we're here, to get cos 27, we've done the construction, so all we need to do is plug in the values that correspond with cos 27. So cos 27 is adjacent over hypotenuse, and that means from 27's perspective, our adjacent is square root of 1 minus p squared over hypotenuse, which is 1, and that'll earn us 2 marks over here. Because then from there, for 5.2.2, it says sine squared 63. So I'm just going to go ahead and rewrite that for us, which means what we have to do is we have to plug in the O over H of sine 63 and then square it. So I've just opened up the brackets over here. I know that I'm going to have to put the opposite over the hypotenuse from 63's perspective, and then we have to square it because there was a square over here. So this means we could have done a co-function, but 63 we have placed over here. So our opposite from 63 is the square root of 1 minus p squared. So I can just go ahead and plug that in. And then our hypotenuse for 63 is still 1 over here, which means all we have to do is square this value. The square of a square root means we just drop the square root, and we have 1 minus p squared. And that just earned us 2 marks over here, which means at this stage for 5.2.3, it says cos 13.5. But for 3 marks, it's a little bit more involved because we don't have 13.5 over here in our triangle. like we did the 27 and the 63. But using our double angle rule for cos 2 alpha over here, we can then expand it because half of 27 is 13.5. So we're just going to write cos 2 13.5 over here, and then we're going to expand it because what we have is cos 2 times 13.5 is cos 27. But we can also see that it's in this setup over here, which means we can expand it into one of these double angles. So I'm just going to make it equal to cos squared 13.5 minus 1, which means that now cos 2 times 13.5 is still cos 27. That is a good thing for us because we need to get the values from this triangle so that we can plug them in terms of p. And then what we can do is rearrange everything on the right side so that cos 13.5 is by itself, just like it is over here. I'm just going to rewrite the right side for us and then we can take it from there. Because as we saw, cos 27 is square root of 1 minus p squared from 5.2.1. So we can just go ahead and write that down. And then what we can do is this negative 1, we can take it over. So it becomes a positive 1 over here. And then we can divide this guy by 2 over there to get rid of the 2 that we have on this side. So we took the negative 1 over, became a positive 1, and then divided by 2 so that there's no longer the 2 on the right side. Okay, which means that we're left with cos squared 13.5. And then all we have to do is take a square root of that and a square root of this guy. And in doing this, we have just square rooted our right side, and cos 13.5 is the square root of square root 1 minus p squared plus 1 divided by 2. And this is how we use our double angle formula to get half of the reference angle in terms of p. So that just earned us 3 marks over there. So then 5.3 says if cos x plus sin x equals k over here, express the following in terms of k, just as we did in terms of p here, but they did not say without the use of a calculator. So this is not a construction, but it is some sort of compound angle, because we can see we have cos x minus 45, and this is quite similar, if not exactly the same, as cos a minus b over here, which means if we usually see a compound angle, it means the best bet is to expand it. So I'm going to go ahead and expand the cos x minus 45 into this form over here so we can see what we have to do next. So as we expand it, we have cos x minus 45, we have our x over there, so we have cos x times cos 45, as we can see with the formula over here, plus sin x multiplied by sin 45. So all we have to do is work on the right side here, and as we can see, they did not say without the use of a calculator, and we're seeing a cos 45 and a sin 45. This should always ring bells in our head because 45 is a special angle, okay? Which means we can just go ahead and plug this in our calculator this time, and for cos x, we keep it the same, but cos 45 is square root of 2 over 2, and then we write plus sin x over here, and sin 45 is also square root of 2 over 2, which means that a very important thing for trig is always looking for some sort of factorizing, because as we can see on this side of our plus sign and on this side of our plus sign, we have square root 2 over 2, and that is common, so we can take that out, which leaves us with a cos x over here on the left side plus a sin x on the right side, which means we're just about done because it said if cos x plus sin x equals k, and we can see a cos x plus a sin x over here, express the following in terms of k, and now we've just expanded it, and we can just substitute our k into this bracket over here and replace the cos x plus sin x. So our final answer is square root of 2 over 2 k, and that just earned us 4 marks. Great job, guys. We've just earned 17 marks and 11 marks to go, and 5.4 now says prove the identity. So pause the video now if you want to try this by yourself before we walk through it, and then we can check the working out together. Otherwise, we're going to jump in and prove this identity. So what we have is cos 2 theta plus 1 over sin 2 theta plus tan theta, and that'll equal 1 over sin theta cos theta. So I'm just going to rewrite this for us. So a reminder that this thing is all about working on the left hand side or the right hand side, and generally we work on the left hand side. So I'm just going to write down LHS so we can start working on that side. So we have a cos 2 theta over here. We're going to work through it from left to right, just as we did with our simplification in 5.1. But a cos 2 theta, we see that it's a double angle over here, and double angles for a cos because we usually leave later because we're not quite sure which one to expand it into yet. So I'm just going to rewrite that one down first. If you see a way to expand it off the bat, by all means expand it and then you can work from there, but I usually leave it later and it works pretty well. So we have cos 2 theta plus 1 over here, and then sine 2 theta can only expand into one form, and that is 2 sine theta cos theta. So I'm just going to go ahead and expand that, because once we've expanded it, things can cancel quite nicely. Okay, and as we can see, a sine theta cos theta is on the left side and the right side. It always helps to see if our moves on the left side potentially move us closer to the remaining values on the right side. And then what we have is tan theta, and a general rule of thumb is to expand your tan theta into sine theta over cos theta. Things will usually cancel once we expand it, which means at this stage, what we're seeing is some sort of LCD, because we would like to simplify everything on top, but we can't yet because on this side, there is a 2 sine theta cos theta, and on this side, there's a cos theta, which means our LCD is 2 sine theta cos theta. And this side has the full LCD, but this side is missing a 2 sine theta. So I'm going to go ahead and write this over here, all over 2 sine theta cos theta, because then from here, as we established, this guy was missing a 2 sine theta. So we're going to multiply it by 2, and then sine theta times by sine theta is sine squared theta. So we have 2 sine squared theta. And then from here, we have cos 2 theta still plus 1. So all we did was multiply this by 2 sine theta at the bottom and at the top. Because now that we're here, it's much easier to see how to expand our cos 2 theta. Because as we can see, we have a 2 sine squared theta over here, and it's often best to try and expand them to the same trig function, which means I'm going to go ahead and pick this middle one over here, the 1 minus 2 sine squared theta, so that my sine squared thetas can simplify. Okay, so cos 2 theta, we're turning into 1 minus 2 sine squared theta, and then we still have our plus 1 over here and the positive 2 sine squared theta over there. Okay, and this is all over 2 sine theta cos theta. Great, because now we can go ahead and simplify our negative 2 sine squared theta and our positive 2 sine squared theta, because these two add up to 0. And then what we have is a 1 plus 1 over here. So we have 2 over 2 sine theta cos theta. And that is great for us because the 2's will go ahead and cancel. And then we have 1 over sine theta cos theta. And this is exactly what we had on the right side to begin with. So we just proved that the left-hand side equals the right-hand side. So we can just go ahead and write that LHS equals RHS. And that just earned us 5 marks over there. And then last question over here, determine the general solution of the equation for 6 marks. Okay, so what we have is 4 sine squared theta equals cos 90 minus 2 theta. So I'm just going to go ahead and rewrite that for us. And usually for general solutions, we're not trying to cancel trig functions. By that, we're not trying to turn this into a sine so we can cancel the sine or take this cos over so that a sine over a cos becomes a tan or anything like that. What we're usually trying to do is get them into the same trig functions, take them to one side, and then see how we can factorize them. Because once things are multiplying in 2 places, they aren't plusing or minusing. Once we have factorized them, we're then going to separate our trig functions and make each of them equal 0, just like we would a quadratic equation. So what that means over here is this cos 90 minus 2 theta. We have our cast diagram over here. 90 is here, minus 2 theta can either place us here or here, depending on the size of our reference angle. But either way, it is positive, which means we have sine 2 theta over here, okay? The next thing we saw previously is that sine 2 theta, we always expanded into 2 sine theta cos theta. So we're going to go ahead and do that now, okay? And this is good for us because even though we have 2 different trig functions, a sine and a cos over here and a sine over here, this still makes it easier for us to factorize in the next step compared to a sine 2 theta, because we can't factorize when something is affecting our angle, okay? So what we're going to do is we're going to take this over here. We have 4 sine squared theta minus 2 sine theta cos theta, and this equals 0, which is a good thing for general solution because now we're in the position to factorize. What we're looking for are numbers and trig functions that are common in both of these. What we can see is that there's a common 2 as well as a common sine, so we can take both of them out, and what we're left with on the left side of our minus sign is a 2 sine theta over there, because 2 times 2 is 4, sine theta times sine theta is sine squared theta, okay? and then a minus will still be here, and then all that's left on the right side is a cos theta, and that will equal 0. And this is great for us because now we have two things multiplying each other, a thing without a bracket, or it could be in a bracket in another scenario, and a thing in a bracket over here, which means what we can do is we can go 2 sine theta equals 0. So we make this side equal 0 just like we would a quadratic equation, and we make this whole bracket equal 0 as well. So we have 2 sine theta minus cos theta equals 0. So if we're going to work on the left side first, if we divide by a 2 over here and a 2 over here, 0 divided by 2 is still 0. So we can just drop the 2 over there, and sine theta equals 0. If we shift sine 0, we get 0 degrees over here. We have our Cartesian plane over here, we have our cast diagram, and we have 0 degrees landing right directly on this x-axis over here, which means if we're going to link that to our trig function to do with a sine graph is something like this, going from 0 to 90 to 180 to 270 to 360, and going all the way up to 1 and down to -1 at the minimum over here, which means that if we're going to place this in our general solution now, our theta equals 0 degrees plus k 180 this time around, because usually sine is k 360, but this time it's k 180 because every 180 degrees there and then there at 360 again, it is hitting the 0 in terms of y. So we can just go ahead and write k 180. K is an element of z, and this side is complete. But then for the right side, there's a little bit more working, because what we have to do is take the cos over, so it becomes positive on the right side. We have 2 sine theta on this side. Then we can go ahead, take our 2 over, so we have cos theta over 2, we have sine theta over here, and then we're going to take our cos theta to the bottom. So we have sine theta over cos theta equals 1 over 2. And this is a good thing for us because sine theta over cos theta this time is tan theta. And this equals 1 over 2 because now, as we can see, we have our cast diagram again. The important thing at this stage is we're trying to get the reference angle, but we always try and place it in the quadrants before we take the reference angle. By that, I mean there's a positive over here, which means we'll be in our third quadrant and our first quadrant. When we're doing sine and cos, this is always important, but tan will always only be in the first quadrant, ignoring the third quadrant because of it having a period of 180. Okay, which means all we have to do here is shift tan 1 over 2, and we have our reference angle of 26,57 degrees. And if we're going to go ahead and place this in quadrant 1, because we don't need quadrant 3 because of our period of 180, all we have to say is theta is 26,57 degrees plus k180 because of the period of a tan graph, and then k is an element of z. And that would be everything we need for our general solution, completing both sides of our quadratic equation, which means theta can be 0 plus k180, k is an element of z, and then it can also be 26,57 degrees plus k180, k is an element of z. And that would be 6 marks over there, 28 marks for this whole section, and 20% of the whole paper. So question 6 says, in the diagram below, f of x equals a sine bx and g of x equals 4 cos x are drawn in the interval. X is an element of negative 180 over here to positive 180 over there included. The graph of f of x passes through 90 degrees and 5 for the maximum height over here, and the graph of g of x passes through 90 and 0, as we can see over here. A over here and B over here are points of intersection of the graphs of f and g. A is negative 141,34 degrees and negative 3,12 for its y value. So then 6.1 says determine the values of A and B. So A and B are two of the unknown values over here on the sine graph, and what helps them most is to interpret the standard forms so we can see what type of shift they've made over here, because our standard sine graph is something like this, because what we have is our maximum at 1, our minimum at -1, we have 0, 90, 180, 270, and 360 degrees over here, which means our standard form for a sine graph is y equals a sine b x plus p in brackets plus q. The a over here has to do with the amplitude, and this a corresponds with this a over here. The b over here has to do with our period, and that is also in line with the b over here. This graph does not have a p, which is a horizontal shift, and this graph also does not have a q, which is a vertical shift. So as we've done in another video, our amplitude for a standard form on our graph is +1. If it was +2, for example, This would mean our maximum at 90 would be positive 2 over here, and then it would go down, intercept at 180, and then at 270 it would be minus 2 over there, and then back up to 360. So positive 2 would double our amplitude. If we were to make it a half, it would be half the amplitude over here. If we had a minus 1, for example, it would reflect this graph over the x-axis. So we'd have a negative 1 over here at 90, up to 180 at 0, at 270 it would go up to 1, and then down to 360 again. So that would be our amplitude in this scenario. Our B has to do with our period, okay? So our period for a sine graph is 360 degrees because we get one crest and one trough, one full cycle in 360 degrees. This is the same for a cos graph, and then tan is a bit different because we have 180 degrees for our period there, which means that our period equals 360 degrees divided by B, which means that if we're dividing it by 1, the period remains 360. If we're dividing it by 2, for example, our period becomes 180 degrees, which means a crest and a trough, a full cycle, will occur in half the time, or half the degrees. So that has to do with our period over here. So a P, for example, is a horizontal shift, and if you were to make it positive 90, for example, it would shift us 90 degrees to the left, which means we're sitting at negative 90 as our starting point, and using our standard form, shifting this 0 and 0 anchored here to start at negative 90 and 0, because then from there the graph will just continue with its standard shape, and then down here at 90, and then 180 would be at negative 1, and then 270 at 0. All we've done is we've shifted each unit to the left because it's a positive by 90 degrees, and horizontal shifts, just like any functions in math paper 1, are backwards, which means a positive moves us to the left and a negative moves us to the right. And we're just trying to see how this relates to our standard form, because then from there, last thing is our positive Q. This is our vertical shift, which means if we make it plus 1, for example, we're going to shift every unit up 1. So this is going to shift up 1, this is going to shift up 1, this is going to shift up 1, and the whole graph is going to move up by 1 unit, which means the shape will be the same. We're just starting from 1 to 2, back down to 1 at 180 degrees, and then at 270, it's going to hit 0, because it's going to move 1 unit up, and then 360 is going to be back at 1, the middle line through our sine graph over there. Great, which means we've worked through what each letter represents here. They can sometimes use different letters in each place, but say now they use a Q over here instead of an A, it is still in the place that affects the amplitude. Same thing if they used a Z in the location of B, it still means it is the thing that affects the period, and so on and so on. But in this scenario, for our A sine BX, we don't have a horizontal shift and we don't have a vertical shift here. We just have to see, based on our standard form, how the amplitude and the period are affected. So using this explanation, try and calculate it yourself, and then we can walk through it together. Because what's happening is 6.1 says determine the values of A and B. We can usually interpret this from the graph, which means that our A value is our amplitude. If we're going to cover up this whole left side, because this whole left side usually makes it a little bit more confusing for us, because what we're looking at here with our standard form that we're going to learn and memorize is that our graph starts at 0 over here and then goes up to 1 with the standard form for our sine graph. What we're seeing here, if we're going to isolate our f of x graph, which is over here, it is starting at 0 and 0, and it is not going down, which means it's not negative. We just have a positive value over here. And then as we can see, this graph at 90 as a value of 5, as we saw, which means this is our sine graph. It is starting at 0 and it is going up to a maximum of 5 instead of a maximum of 1, which means that our A value just equals 5 over there. Because we've identified our starting point, we see that the shape is similar, and then at 90 degrees still, as we can see here, it is at its maximum. But this time, instead of a maximum of 1, it's at a maximum of 5. Okay, so all we have to do is write A equals 5 over there. We've earned 1 mark, and then B has to do with our period. A reminder that our period changes how many cycles we get in the same amount of degrees, which means that in 360 degrees, we'll have 2 crests and 2 troughs over there. So it's how compressed or how stretched the graph is. And as we can see over here, going from 0 to 90 at the maximum, here it's also going from 0 to 90, which means we haven't halved our period, we haven't affected our period at all, because our maximum, based off of our original graph, is still 90 over there. It isn't sitting at 45 degrees, for example, or anything like that, which means our maximum is at 90 and the maximum here is at 90, which means our period over there, our B value, is just 1. And that just earned us 2 marks over there. And then 6.2 over here says the graph of g of x is shifted 30 degrees to the right and 2 units vertically down to form the graph of h of x. Determine the equation of h of x. So a cos graph over here, the standard form is something like this, starting with half a crest at 1, going down for a full trough, and then having the other half of the crest on the side. This is also at a maximum of 1 and a minimum of -1, and then we have 0 degrees here, 90, 180, 270 intersecting there, and then 360 degrees at our maximum for 1 again. Okay, which means this is our standard form, and our standard equation is y equals a cos b in brackets x plus p close brackets plus q. Exactly the same as our sine form over here. Each placeholder affects it exactly the same, our amplitude, our period, our horizontal shift, and our vertical shift over there. And all of these values are a 1 for our amplitude, a 1 for our b, a plus 0 in the standard form for our p, and a plus 0 for our standard form of our q. Okay, which means now in this scenario, they're saying the graph of g of x is shifted 30 degrees to the right and 2 units vertically down to form the graph of h of x. Determine the equation of h of x. So as we can see, g of x is 4 cos x, so we can just go ahead and write that. And then in order to do the transformation from g of x to h of x, we have to make the following moves, because they didn't affect the amplitude, they didn't reflect it over the x-axis or adjust the maximum or minimum, which means we still have the 4 over here, we still have our cos, because we haven't changed it from cos to sine, or any cofunction, which means that to deal with the shifted 30 units to the right, just like we explained for the sine graph earlier, we're going to have to open up our brackets here, write down x again, and then to the right is negative, and then we just have to put the amount of degrees that they asked for over here. So x minus 30 would shift our graph's starting point from the origin 30 degrees to the right. So we've dealt with that, and then 2 units vertically down means that we are going to shift it down 2 units, which means ultimately we had a graph like this over here, and if we're going to see how this shift actually looks on this graph over here, it always makes the most sense to make your Q shift first and then adjust any other shifts that you may have, okay? Which means that we're here from 4, we're going to shift it down 2 units, and then from there, we're going to shift it 30 degrees to the right, which means that this 4 over here has translated and is now located here, which means that if we're going to look at the next point over here, let's say this 60 degrees and 2, what we're doing is we're shifting it 2 units down and then 30 degrees over here. And then at 90, we're going to move it 2 units down and 30 degrees to the right. And then the 60 over here, we're going to move it 2 units down and then 30 degrees to the right, which means we have a graph going like this, and like this. And then this over here, we're going to move it 2 units down and 30 degrees to the right, and then we have our minimum at -4 and 210 degrees over here. Then as we'll see here, the -60 will move it 2 units down and 30 units to the right. So we're dealing with this over here, and this graph is going to curve down like that. And that is how we would adjust this if we needed to draw it in another question. But we still have the same amplitude, we've just shifted it 30 degrees to the right and 2 units vertically down, and then transformed each point and then connected them. And that just earned us 2 marks over there to determine the equation of h of x. Because then from there, for 6.3, it says calculate the minimum value of 8 over g of x in the interval of x is an element of -60 over here to +60 over there. So this is an interesting type of question. A minimum, we're usually looking at the lowest value. So if we're going to look at the lowest value in -60 for g of x, our cos graph over here, we have a +2 here, and as we trace it, we're going from a +2 to a +4 to a +2. And usually a minimum means we just take the lowest value in that little range, and 2 would be the lowest value there. But this is a bit different because now we've set it up in an equation, and they want the minimum value of this whole equation, this whole expression, which means the way that we're going to get the minimum in this scenario is to take the maximum over here because of where the g of x is located. Because what we have is 8 over g of x, and we want the minimum value of this whole expression. And the way that we can get the minimum value of this whole expression is to put the the maximum or the biggest value in the denominator, because then we're going to divide 8 by whatever the biggest value is, and this whole value will become the minimum, which means that our maximum value from negative 60 degrees to positive 60 degrees in this interval that they've given us is a positive 4 over here, which means all we have to do is write 8 divided by 4, and we'll see that the absolute minimum value in this specific scenario is 2 over here, because we've plugged in the maximum so that we can get the minimum of the whole expression. And all we had to do was write down our answer there, and that would earn us 1 mark. From there, we have 6.4, and it says if A is negative 141,34 degrees and negative 3,12, determine the coordinates of B. So B over here is the other intersection point. As they said in the initial writing, A and B are points of intersection of both of the graphs. Okay, so with this, determine the coordinates of B for 2 marks. This is also just a question that we have to interpret, because what happens is that intersection points between sine and cos graphs happen every 180 degrees, which means, as we can see here, we're sitting at minus 141,34 degrees for the x value in terms of degrees, and the b value here is sitting just after 30 degrees over there. And we don't usually want to equate these two things and try and solve for them. We by all means can, because if we make them equal, we can potentially make an expression, but we usually don't have to, because if we know that a sine and a cos graph intersect every 180 degrees, provided that there's no shift in their periods, every 180 degrees, these graphs will intercept, which means all we have to do for our b value here is write b is minus 141,34 plus 180. And we have 38,66 degrees. If we put that in our calculator, is the point of intersection for the x value. And as we can see, it's a little bit past 30, and this makes sense. And then from there, all we have to do for our y value is that the y value is a complete reflection, because as we move down here, 180 degrees later, we'll be at the same height, but positive. And then again, 180 degrees later, we'll be at the same height, but then negative, because of how the crests and the troughs interact with each other, which means all we have to do for our y value is write this value over here, but positive. So we can write positive 3,12, and that would earn us 2 marks over there. And then from there, 6.5 says, for what values of k will f of x equal k have no real solutions? So what we have for our f of x graph is 5 sine x over there. Okay, as we calculated the a value in the beginning as 5 and the b value as 1. Here we have our equation for our sine graph, and then what they want is the f of x equal k having no real solutions. So no real solutions means that this graph does not have any x values because it does not intercept with the x-axis, which means what we can do whenever we see k is we want to move it over and see how it affects our y-intercept. Just like we saw in the analytical geometry question earlier, because we have 5 sine x, we take our k over and it becomes a negative k, and this equals 0, okay? And what we need to see is what type of shift can we make to the y-intercept so that this graph does not intercept with the x-axis at all, because that's what no real solutions means. It means that if we were to do a quadratic, there would be no values for x, which means that if we're going to interpret this, we're going to run through a couple of scenarios and see what values of k will work. Because say now we make k minus 4, for example. We're going to move this whole graph here to start from 0 to minus 4. We're going to move this 90 down to 1 over here by 4 units. And then we're going to move this 180 degrees down to negative 4 over there, which means we have a graph something like this. And as we can see, there'll still be 2 solutions over here, 2 x-intercepts. But if we move this graph, let's say, for example, 6 units down, we move 0 down to negative 6. We move 90 and 5 down by 6 units, which means it's intercepting at 90 and negative 1, and then 180 degrees back down to negative 6 over there. What we have is a graph going like this and like this, which means that it is currently not intercepting with the x-axis at all, and it won't intercept on this side either, which means that k just has to be any value greater than 5 in this scenario, because what we're doing is we're going to keep the negative here, and then we're plugging in any value that is greater than 5. Let's say it's 5,1, for example, and then we have 5 sine x minus positive 5,1. We have 5 sine x minus 5,1. And as soon as we're a little bit past 5 over here, this graph will not intercept at all with the x-axis, because if it was exactly at 5, it would move all the way up and hit 90 degrees at 0 over here, and then down to 5 like that. As soon as we shift this y-intercept down a little bit more from 5, we will not intersect with the x-axis at all. So that is the first scenario, earning us 1 mark over there. Because k is greater than 5, we sub in any value that is greater than 5, and it becomes minus that value, and then we're going to shift this graph down so that it does not intersect with the x-axis at all. Because that is only one part of it. What we were looking at was this graph over here. We're looking at the crest on this side, on the positive side for our degrees, but we were not looking at the trough on the negative side of our degrees, which means that if we're going to do the same thing over here and shift this negative 90 and negative 5 up 5 units over there, this minus 180 up 5 units over there, and the 0 once again up 5 units over there, we have a graph on this side that is still intercepting once. Means that it has a real solution. But it's exactly the same as we were chatting about here, is that as soon as we move it slightly more than 5, for example, it will not be intercepting with the x-axis at all, which means that here there will not be any real solutions there either, which means that in this scenario we had k is greater than 5, but then we also potentially have k is less than minus 5, because if we have any value that is less than minus 5, so now we have minus 5 comma 1, for example, we have 5 sine x there still, then we're going to have minus 5 comma 1, and that becomes a positive 5 comma 1, and then what we were just looking at is we've moved this whole maximum up more than 5 units so that it's no longer touching the x-axis at all. And with these two answers over here, this would earn us 2 marks for this question, calculating the values of k that will have no real solutions when f of x equals k over there. Cool. Let me know if there are any questions on this one in the comments below, and then I can explain it further if need be. And then from there, last question over here, 6.6 says, use the graphs to determine the values of x in the interval of x is an element of minus 180 degrees to positive 180 degrees, included for both. So it is just this whole area here that they mapped out for us from negative 180 to positive 180. So they're saying for which 6.6.1, f of x is less than g of x. So our f of x graph over here is less than our g of x graph over here, which means f of x is here and g of x is over here. And what we need to look at is whether f of x is less than g of x in terms of y, which means that we need to see where the yellow line is below the red line over there. And it is below the red line in this whole interval from here to here, because over here, the yellow line is above the red line, the g of x, and over here the yellow line is above the red line. But what we want is where the g of x, the red line, is above the f of x, the yellow line, which means that it is just in the range over here in terms of x, where x is an element of not including, because there's no line underneath here, minus 141,34, and the other point of intersection over here at B, which we calculated earlier, of 38,66, and also not included because there's no equal to sign underneath our inequality, which means we just earned 2 marks over there. And then very last question, 6.6.2 says where the f of the first derivative of x, our sine graph, multiplied by g of x is greater than or equal to 0. Okay, so I'm just going to rewrite this for us. So we have our f first derivative of x multiplied by g of x is greater than or equal to 0. So seeing a derivative in a trig question can really throw us off. But something we have to know is that the first derivative of a sine graph is just turning it into cos. It is basically doing a cofunction in our 90 plus quadrant, because it means that we have 0 degrees here, 90 over here, 180, 270. And what we're doing for a derivative of a trig function is basically treating it exactly the same as going 90 plus x, which means that a sine 90 plus x, sine is already positive here, so we take the positive out and then we just change it to cos of x. And then cos 90 plus x, cos is negative in the sine quadrant, so we take a negative out and then we just change it to sine x. So we have negative sine x over there. So quite different, not something we're usually exposed to, but that means for this 5 sine x, if we're doing the cofunction of our f of x over here, it's going to become sine 90 plus x, which becomes positive cos x. And we just leave the 5 outside because we're not going to affect the amplitude. So it just becomes 5 cos x over there. And then what we're doing is we're multiplying this by g of x, which was 4 cos x. And we have have our 4 cos x over here, and where they are greater than or equal to 0, which means that we are turning these graphs into very similar graphs, just with a slightly different amplitude, which means if we're going to look here and draw a new graph for what f of x now represents, we have a graph that is going from here down to 90, down to -5 over there, and then down to 90, down to -5 over here, which means that they're almost identical. So if we're going to look at how they relate in terms of multiplication, the only options we can have is where this guy is positive and this guy is positive, because a positive times a positive is positive and greater than 0, or a negative multiplied by a negative, because a negative multiplied by a negative is also greater than 0. So usually we would try and segment where the intersection points are with the x-axes, so we can see how they relate to each other in terms of being negative and positive. But in this scenario, they're both negative over here, which means they're positive, because a negative times a negative is positive. Once they cross the -90, they'll both be positive from -90 to +90, which means a positive times a positive will also be greater than 0. And then again on this side, once we're past 90 and below our x-axis, they'll both be negative, and a negative times a negative is positive, which means that there's not as much segmenting in this scenario compared to some other questions, because the whole domain from -180 to +180 will all be greater than or equal to 0, because they're below the x-axis and above the x-axis at the same time as we move from left to right, which means that the difficult part of this was knowing that our derivative of our sine graph is just a cofunction, a 90 plus x, which means now we have the exact same forms here, and all we have to write is that x is an element of including -180 degrees to 180 degrees included over there, because at each step they are either below the x-axis at 0 or above the x-axis at the exact same time. So there's no interaction difference, and it means that a negative times a negative is positive, 0 times 0 is 0, which is included here, positive times positive is positive, and this repeats as we move all the way to 180, which means that this is the interval where 5 cos x multiplied by 4 cos x is greater than or equal to 0, and this will earn us 2 marks over there. Let me know if that one makes sense as well in the comments below, and then I can answer any questions you may have there as well. So question 7 here says, in the diagram below, TQR represents 3 points in a horizontal plane on a sports field. PQ over here represents a vertical flagpole. The angle of elevation at the top of the pole from R, so the top of the pole from R is equal to theta. T equals theta here, angle T. TQ equals TR equals Y, which means this is an isosceles triangle. Then QR equals x units over there, and TQR, angle Q over here for TQR in our triangle on the horizontal plane, equals alpha over there. Okay, so each question leads into the next question. So 7.1 says, express theta over here in terms of alpha and show that sine theta equals sine 2 alpha for 2 marks. So this means we're going to be working in triangle TQR over here, because we have an isosceles triangle that was given to us, which means that because this is an isosceles triangle, this angle TRQ over there is also equal to alpha over there, because angles op equals sides. Okay, we don't have to put any reasons, but this is how we're going to prove this, because theta over here equals 180 degrees because of interior angles of a triangle minus 2 alpha over there, which means that this one's a bit different, because what we have to do now is just introduce sine to both sides. So we have sine theta equals sine 180 degrees minus 2 alpha, which means that all we have to do here is do our working of sine theta equals sine 180 degrees minus 2 of alpha, which means it can place us in our sine quadrant or our all quadrant, but either way it is positive. So therefore sine theta equals sine 2 alpha. And that would earn us 2 marks over there, because we added sine, because we are taking the reference point of the opposite over hypotenuse from the same angle, because theta represents 180 minus 2 alpha, which means we can just introduce sine to both sides and then solve for this equation in terms of sine. Because now we expressed theta in terms of alpha, and we showed that sine theta equals sine 2 alpha. From there, 7.2, it's saying, hence prove that triangle PQR is PR equals 2y cos alpha over cos of theta. So for 4 marks. Whenever they say hence, it's very important that if we could not calculate this in 7.1, we would then use this sine theta equals sine 2 alpha in this next question. Okay, so what we're doing for 7.2 and any question that is trying to prove some sort of ratio like this, or some side in terms of the lengths, the angles, and the trig functions, it means that we are looking for the common side, okay? And the common side between these two triangles is this side here, this QR, which means we have just started in this triangle, and we're going to see now how PQR, how we can get the angles from here and the sides from here in terms of QR, okay? Because ultimately what they want is PR over here, and the only way we can get PR into this triangle TQR at the bottom is to get PR in terms of QR, okay? So if we're going to work with our trig and triangles for our PQR over here, we're going to use our sine rule for 4 marks, okay? Because it means we have A over sine A and B over sine B. A reminder that the sine rule, the A is the length of the side opposite the angle that we're dealing with, which means that if we want PR, we're going to have to put PR over here. The angle opposite PR is sine of 90, and as we'll see in our calculator, sine of 90 is always equal to 1, okay? And then the side that we're dealing with here is our x over there, because we want to get QR here. And then the angle that we're dealing with is this angle P over here. And what this is for P is 180 degrees minus 90 minus theta, which will leave us with a 90 minus theta for the angle of P over here, which is a good thing for us because sine 90 minus theta is always a cofunction, which means that we have this guy over here, we can plug it in, sine 90 minus theta, and then we can solve for it because this time PR is going to remain. Sine 90 in our calculator is just 1, and then what we have is x over sine 90 minus theta based on our cofunctions, places us in our all quadrant. So sine 90 minus theta becomes cos theta over here, and then we want to get x by itself so that we can sub QR into our triangle TQR and get our PR into that equation, which means we're going to take the cos theta up, and we have PR multiplied by cos theta equals x, which means we now have x that we can do trig and triangles again for our triangle TQR and then get our PR into this triangle, which means that if we're going to do the sine rule here for QRT, what we're going to do is we're going to sub in x, this side here, over sine of theta over there, and make that equal y over here over sine of alpha over there. What we can then do is we can substitute the PR over cos theta into the location of x over here, because from triangle PQR, we established that x equals PR over cos theta. So it's basically a simultaneous equation between two different triangles and the common side, okay? Which means we have PR times cos theta over sine theta equals y over sine alpha. And now what we need to do is isolate for PR so that PR is by itself and that everything else is on the other side to the right of our equal sign, which means what we can do is we can cross multiply our sine theta up top with the y over there. So we have sine theta. We can then multiply down our cos theta to join our sine alpha over there. So we have sine alpha multiplied by cos theta, and then PR is by itself on the left side. Okay, and we have this guy over here, and very often in a question like this, we would have some sort of tan where we take our sine theta over cos theta and turn them into tan. But in this scenario, we don't have a tan, and we have a couple of things missing right now because the cos theta needs to stay at the bottom. There also is not any sine alpha at the bottom. The sine theta at the top is no longer there. There's a cos alpha over there. The y is here, so that's good. And then there's no 2 over here. And this is where our hence comes in, because hence proving that sine theta equals sine 2 alpha is exactly what we need to do, because the sine theta here, we're going to turn that into sine 2 alpha, and then we're going to take it from there because we're almost done. One thing to keep in mind is that sine 2 alpha is a double angle, which means we're going to go ahead and convert that into 2 sine alpha cos alpha. So it means that we have PR equals y times 2 sine alpha cos alpha, because a double angle can come into play in normal trig graphs, and trig and triangles. And then that is over sine of alpha multiplied by cos of theta, which means at this stage, we can just cancel things nicely because sine alpha cancels with sine alpha over here, and we're left with exactly what we want. We can just rearrange it. So we have 2y, so I can just rearrange the 2 and the y. So we have 2 multiplied by y. Cos of alpha is remaining at the top, and this is over cos theta at the bottom by itself, which is exactly what we have here. It says hence prove that triangle PQR is PR equals 2y cos alpha over cos theta. And this is what we've just proven here, where PR equals 2y cos alpha over cos theta. Great job, guys. That just earned us 4 marks over there. And the whole procedure is always trying to find how we can get to the common side in terms of the angles we have in the one triangle, and then equate that to the other side in terms of the angles it has. And the most common approach is to use the sine rule first, and then if it's worth more marks than that, there's generally a cos rule involved, and otherwise only starting with area if they've given us information in the top to do with area. But otherwise, the sine rule is our best bet to go forward to get the one side in terms of the other side, so we can then find the link between the two different triangles. And then 7.3 over here, last question of this section, it says if alpha equals 49 degrees over there, x equals 20 meters, and y equals 15 meters, calculate the area triangle TQR. So TQR is the triangle on the base, the horizontal plane, and our area formula for a triangle is half AB sine C, which means we can just go ahead and write that down. Usually in these questions, the thing we calculated in 7.2 is the equation that we'll use and substitute these values into. But this time around, it isn't the case because we are calculating area and there were no questions to do with area previously. But if we're going to look in triangle TQR, we're going to have to set this up that we have the angle in between the two sides. They gave us the x value here and the y value here, and they gave us the angle of alpha, which means that we're going to take half of side TQ multiplied by side RQ multiplied by sine of alpha. And then from there, as we can see, TQ represents y, and y was given to us as 15 meters. So we can just plug that in. So we have a half multiplied by 15 multiplied by RQ. RQ represents x over here. X was given to us as 20 meters. So we can plug that in. And then sine of alpha. Alpha was given as 49 degrees. So we're just going to write sine of 49. From here, all we have to do is plug this in our calculator, and we have 113,21 degrees. And that'll be our final answer for the area of triangle TQR. Great job, guys. And that would earn us 3 marks over there, 9 marks for this whole section. So question 8 here says, in the diagram below, O is the center of a circle. So that is important for us, which means any lines from O are radii. So we have a radii here and a radii here. That's important. A, B, and D are points on the circle. BC is a tangent. So we're going to highlight BC here as a tangent so that we can see if any tangent rules apply. So BC is a tangent to the circle at B over here, and DBC is 22,5 degrees. Chord AD, so it's not cutting through the center of the circle, is produced to C, so its angles on a straight line over here, such that CD over here equals BD as they mentioned. So we can already see that CD over here is equal to BD, which means that 8.1 says determine giving reasons the size of 8.1.1 angle A1 for 2 marks. So they want angle A1 over here. So for 2 marks, we usually have to find the most direct approach from this information that's been given to us to get directly to the angle that they're asking for. Because what we're going to see is that each thing we calculate here, we're going to use to calculate the next question. So how can we go directly from CBD, this 22,5 degrees here, to angle A1? And something to keep in mind whenever we have a tangent, and that's meeting a triangle with all 3 corners touching the circumference of the circle, is that we can jump into the triangle and then to the furthest side away from it. So if we have a tangent meeting a triangle over here, it means that this B, this 22,5 degrees, equals A1, because DBC equals A1 equals 22,5 degrees because of tan chord theorem. When we're usually not seeing a thing, it usually has to do with tan chord theorem. It's quite an easy theorem to miss, which just means we have to see for a tangent and a triangle, and then it means that we are jumping into this angle here and then to the furthest side opposite from it. So here into there. If our tangent was continued over here, for example, this angle would be jumping into the triangle and then to the opposite side over there for D1. But that just means we earn 2 marks over there, showing that A1 is 22,5 degrees for 1 mark, and then the other mark for the tan chord theorem reason over there. 8.1.2 then says D1, because what we can now do is use the information here, CD is equal to DB. So we don't have to write that it's been given. It's only 2 marks, which means we can just use that information to show that angle C here will equal angle B here, because D CB equals DBC equals 22,5 degrees. Because if CD equals DB, this angle equals this angle, because angles op equal sides, which is great for us because now we know that angle C equals 22,5 degrees. And if we want D1, like they were asking for, D1 is the exterior angle of a triangle, which means that D1 equals C plus B over here. We could do interior angles of a triangle, get D2, and then do angles on a straight line to get D1. I know that's often an easier way that most of my students prefer, but if we do see it straight away, D1 equals C plus B over there, which means that D1 equals angle C plus DBC equals 45 degrees, because this one is 22,5, this one is 22,5. Together they add up to 45 degrees, and this is because exterior angle of triangle. And that just earned us 2 marks over there. 8.1.3 says calculate the angle of B2. So B2 is over here. It is inside this triangle. But what's most important and something to keep in mind is that we're always trying to look at points where the tangent is interacting with a radius. Because a tan meeting a radius is a reason itself, and that will equal 90 degrees over here because of tan perp rad, which means that if we have the 22,5 over here, calculating B2 will be the remaining portion of 90 degrees, which means that CBO equals 90 degrees because of tan perp rad. And then what we can say for B2, B2 equals 90 minus 22,5 degrees. This is just calculating now. We didn't have to say again that angle B over here equals 22,5. So we just need to show our working because we wrote down our statement and our reason. Now this is just a calculation, which means that B2 is 67,5 degrees. And that would earn us 2 marks over there. Last question for 8.1. 8.1.4 says calculate the value of O1 over there. So O1 is the angle over here, and the easiest way to calculate O1 is to do angle at center equals 2 times angle at circumference. So usually in a scenario like this, we look for a bow tie where all 4 corners touch the circumference, which means if we're seeing a bow tie and all 4 corners are touching the circumference, it means we have angles in same segment, which means that this angle over here equals this angle over here, and this angle over here equals this angle over here. But in this scenario, we have a bow tie, but not all 4 corners are touching the circumference. We have a bow tie like this, but this O here is not touching the circumference over there, which means that this guy is angle at center. This angle O1 equals 2 times the angle at the circumference for D1. So they're very similar. All we're looking for here is a bow tie that does not have all 4 points touching the circumference compared to the angles in the same segment where all 4 points are touching the circle, which means that all we have to write is that O1 equals 2 times D1 over there, because angle at center equals 2 times angle at circumference, which means that D1 we calculated as 45 degrees earlier, and that means that O1 is 90. So O1 equals 2 times D1, 2 times 45 is 90 degrees, and therefore O1 equals 90 degrees. And that would earn us 2 marks over there. Great, because then 8.2 over here says prove giving reasons that OA, so OA over here, is parallel to CB. So we need to prove parallel. So the best way to prove parallel is to work with the F, the U, or the N from our funky X. I'm not sure if your guys' teachers teach you this, but these are the important grade 10 geometry rules, which means that the F, the U, and the N all have to do with parallel lines over here. The K is angles on a straight line, the Y is angles around a point, the X is vertically opposite angles, but now we can either look for an F, which is corresponding angles that are equal. So this angle will equal this angle here. Cointerior means that they add up to 180 degrees, and then alternating angles means that this angle is equal to this angle. Okay, but now we're proving the converse, because what we need to do is look for an F, a U, or an N and find the equal angles here and equal angles here, or these angles adding up to 180 degrees. And then because of that, we can then say, therefore, these guys are parallel. The most common ones to look for in a situation like this is our F here and our N here. And I can already see an N based off of the information we calculated in 8.1.4 is that we have an N over here. If we're trying to prove that OA is parallel to BC, which means that we're looking for the angle in between the 2 lines. And as we can see, the angle in between the 2 lines is the 90 degrees from O1 and the 90 degrees of CBO over here that we calculated earlier, which means we've already done all the working out. This is only 2 marks. So all we have to write is that O1 equals 90 degrees because this was proven here in 8.1.4. So we can just write proven, and CBO equals 90 degrees. We could either say proven or we could say tan perp rad over there, and therefore angle O1 equals angle CBO, and that is exactly what we needed to prove that OA is parallel to BC, because OA is parallel to BC now, because these angles are equal, and that is because alt angles equal. Great, and that just earned us 2 marks over there, because now 8.3 over here, last question says, it is further given that the radius of the circle, so the radius OA and the radius OB is 12 units. 12 units and 12 units. Calculate the length of BC for 4 marks. So BC over here, we need this length for 4 marks. So if we're going to look in triangle OBA over here, and we have the lengths of 2 radii, and we have a 90 degrees here at our O1, it means that we can do Pythag to get BA. So we'll do that first, and then we'll see why we need to get BA. Because OA squared plus OB squared equals AB squared because of Pythag. And OA was given as 12 units. 12 units squared becomes 144, plus OB is 12 units. 12 units squared is also 144, and this equals AB squared, what we want, which means that AB is the square root of 288 units, and that will equal 12 surd 2. So generally just leave it in surd form, don't try and round to decimals. It's usually easier to handle it like this, which means AB equals that. Calculating the length of BC then will be easy for us, provided we're seeing that we're working with triangle CBA, and as we know, this angle C equals this angle A1 over here, which means that this line BA will equal this line BC over there. So all we have to do is write C equals A1 proven, because we already proved that earlier, and then therefore BA equals BC, or AB, as we wrote it here earlier, equals CB, because sides op equal angles. So sides op equal angles. So we have equal angles, the sides opposite those angles are equal. So we always write what we see. We're saying the sides opposite the equal angles, and that's the reason for why they are equal. And therefore all we need to do is AB equals 12 surd 2, and that means that CB, or how they want it here, the length of BC, equals 12 surd 2 as well. And that would earn us 4 marks over there and 14 marks for this whole section. So question 9 here says, in the diagram below, the diameter BE, so diameter is always important for us, which means that we are passing through the origin, which means we can use radii rules and diameter rules. The diameter BE of a circle O is produced to D. So it means that it is extended on a straight line. DA is a tangent to the circle, and CD over here is perpendicular to BD over there, which means we have a 90 degrees over here, as has been given. They also then say AC and BC cut the circle at E and F respectively. OF and EF are drawn. So quite a lot of information, but the highlighted lines over here and the angle that's been given are usually what we're going to start our question with. Because 9.1 here says prove with reasons that A, B, C, D is a cyclic quad, which means that if we had a circle like this, all 4 points would be touching, which means that we have to prove something about A, B, C, D so that we can prove that it's a cyclic quad, and therefore draw a circle around it like this with all 4 points touching the circumference, which means that the most common proofs for a cyclic quad, there are 4 of them, is that if we have a line like this and we have a triangle over here, if this angle equals this angle, we can then therefore prove the converse of tan chord theorem, which means that because this is equal to this, we can therefore draw a circle around all 3 points, and therefore has the properties of a triangle in a circle. This would be for a triangle, which means there'd probably be another portion somewhere that is looking something like this, so that we are dealing with some sort of cyclic quadrilateral. The second converse is some sort of exterior angle of a cyclic quad, because if we have a line like this and this angle equals this angle, then therefore we have a converse of exterior angle of cyclic quad. And this means that we can draw a perfect circle around our quadrilateral, touching all 4 points over there. From there, a common third one is to prove opposite angles are supplementary. So if this angle plus this angle add up to 180 degrees, then therefore we can also draw a circle around this quadrilateral, touching all 4 points. And this is called converse opposite angles of cyclic quad, which means we can look for either of these three in this scenario, but the proof that we are going to use has to do with converse angles in same segment. Because if we have a bow tie, as we can see over here, there are quite a few bow ties in the scenario, and we can prove that this angle equals this angle. We can therefore then say that there is a perfect circle that we can draw around all 4 points. Say now it's a quadrilateral like this, and we have the bow tie over there. Then therefore it is converse angles in same seg, which is the same segment. Okay, so these are the 4 different scenarios we often look for, and we are going to use this 4th one over here. The 4th one works best because we were given an angle 90 over here, which means if we know D2 is 90, it means that we have to prove that A2 is 90 as well. And A2 is 90 because we have angle in a semicircle over here. If ever we have a diameter, we have to look for angle in semicircle, because we have a right angle triangle inside our semicircle. By that, the semicircle is this whole side here. We have a right angle triangle in this part of the semicircle, and it means that this whole side we're ignoring, we're covering it up, so we can just look at the 1/2 of the semicircle. That is just helping us look for the 90 degrees and understand the reason of angle in semicircle, because we're just dealing with a right angle triangle in the 1/2 of the circle, the semicircle, which means we can just go ahead and write A2 equals 90 degrees because angle in semicircle, and D2 equals 90 degrees because given, which means that D2 over here equals A2 over there. And if we're looking at the bow tie that we're working in, we have our bow tie over here, which means that here would be B1 equaling C2, and here, as we can see and have just proved, D2 equals A2. So we write A2 equals D2, and therefore A, B, C, D is cyclic quad, because as we mentioned over here, our reason is converse angles in same segment, and that would earn us 3 marks, because now that D2 equals A2, therefore we could draw this circle around it with all 4 points, A, B, C, D, all touching the circumference. Because then from there, 9.2 says, prove with reasons that BD bisects ABC, which means that we have to prove that B1 equals B2, and it usually is quite helpful to put them in terms of X so that we can see which other angles might also relate to X. Because what we now have is we're trying to find a common angle that links to both of them so that we can prove that B1 equals B2. Okay, and the best thing to look at right now, we've used the 90 degrees here. We've worked with that. We've worked with the yellow line, the diameter. We have not yet worked with our tangent, which means we're going to work with our tangent now. And what we can see is that A3 over here will equal B1 over there. Just like the previous question, question 8, we are looking for tan chord theorem. And if ever we can't see the reason that we're going for, it's probably tan chord theorem, a very easy one to miss, which means that A3 over here, we're jumping into this triangle, AEB, and then to the opposite angle of that triangle, which means that A3 over here equals X as well. So A3 equals B1 because of tan chord theorem equals X because of tan chord theorem. And then from there, we proved 9.1 that ABCD is a cyclic quad for good reason, is because now we can use the properties of that cyclic quadrilateral. And as we can see, just like the previous one worked with the bow tie, we can also see that there's a bow tie happening this way in our previous cyclic quad, which means that we're just looking in the pink bow tie over here. We see that A3 is equal to B2 as well, because A3 over here is that part of the bow tie and A2 is this part of the bow tie, which means we can write A3 equals B2 equals X because of angles in same segment, which means that if A3 equals B1 and A3 equals B2, therefore B1 equals B2, which means that B1 equals B2 equals X. And there is no reason for that. That is just a proof. We have said that A3 equals B1 and A3 equals B2, and therefore B1 equals B2. And with that, if B1 equals B2, we have proven that BD over here bisects ABC, bisects the corner, cuts it perfectly in half, so that B1 equals B2 over there. So we can just write down our conclusion. BD bisects ABC. And that would earn us 3 marks over there. And then last question, 9.3 says, prove prove with reasons that EC over here is a tangent to circle OEF. So proving with reasons that EC is a tangent to circle OEF, which means we're now dealing with another circle here with OE and F all touching the circumference here. Okay, and what we need to prove is that EC over here is a tangent to this circle, that it is not cutting through over there. Okay, and as we were chatting about earlier with proofs for cyclic quads, we're usually looking for converse angles in same segment, converse exterior angle of a cyclic quad, converse opposite angle supplementary, or converse tan chord theorem. Because what we can see inside the circle over here, OE and F is a triangle, which means the interaction between a triangle and a tangent has to do with our tan chord theorem. Because if this angle equals this angle, then therefore we can draw a circle around the triangle over there, like we're trying to prove here. And in this scenario, we're not trying to prove a circle, we're trying to prove that it is a tangent and not cutting through that circle. Which means that if we're going to look at the circle over here, the angle that we're trying to prove, or the easiest angle that we're trying to prove, is that E3 over here equals O1 over there. And we're going to see why that is the case based off of our previous calculations. Because what we have to do is calculate O1 in terms of x like we did earlier, and then E3 also in terms of x, and then we can see that O1 will equal E3, and then we can say that EC is therefore a tangent to circle OEF. But if we're going to start with O1 and how it relates to our previous calculations, we can see that O1 is 2 times the angle of B2. Because what we have is an arrow over here. Whenever we're dealing with an arrow like this angle here is 2 times the angle at the circumference. Angle at center equals 2 times angle at circumference. And that is exactly what we're seeing here and all the way up to B2. The only difference this time is that they are joined at the bottom, which doesn't change the meaning at all. It just means we're dealing with something like this, and the reason is still the same, which means that O1 equals 2 times B2, which equals 2x, because O1 equals 2 times B2, which equals 2x over there. The reason over here is angle at center equals 2 times angle at circumference, which means if we're going to put a value in here, we now know that it is 2x over there, which means the whole objective is to prove E3 equals O1 here, which means that E3 is also equal to 2x. We just need to know why, because if we're going to look at our original circle and we're going to look at the cyclic quadrilateral EABF over here, we can see that E3 over here is the exterior angle of our cyclic quad, which means that E3 over here is the angle outside our circle, and E3 equals B1 plus B2, because exterior angle of a cyclic quad jumps into the angle in our cyclic quad and then equals its opposite angle, which means that E3 equals B1 plus B2 equals 2x. And the reason for this one is exterior angle cyclic quad, which means that O1 equals E3, and that is exactly what we wanted. O1 equals E3 equals 2x, because O1 equals 2b2, which equals 2x, and E3 equals B1 plus B2, which equals 2x, and therefore O1 equals E3, which equals 2x. And as we can see, O1 is 2x, E3 is 2x, which means that EC is a tangent to circle OEF. So we can just write our conclusion, and that would earn us 4 marks over there and 10 marks for this whole section. So it says 10.1 in the diagram below, triangle ABC over here is drawn with DE parallel to BC, as we can see over here. It says prove the theorem, which states that AD over DB equals AE over EC. Okay, so what we have to do is start with a construction. So we're going to draw a line all the way up from E until it comes into contact with AD over here, and it is perpendicular. So we're going to call this line H1 because it is our perpendicular height 1 over there. The line from D we're going to draw up until it hits AB, and it is also going to be a perpendicular height over here, and we're going to call that H2. From there, we're also going to have to join E to B and D to C. Imagine it was straight. So we've got these straight lines over here, and we have also connected them. So on the rubric, we won't get any marks if we haven't done these constructions. So I'm just going to go ahead and write the constructions that we did. We have perpendicular height H1 on AD, as we can see over here, and we also have perpendicular height H2 on AE, as we can see over there. We also joined DC and BE, as we can see here, DC and BE over there. From here, we're going to have to start with our first 2 triangles, and the first statement we're going to say is triangle ADE over here, triangle ADE over here, over triangle DEB over there, which means we're just going to write that now. So area of triangle ADE over area of triangle DBE. So once we're here, we're just going to expand our formula to actually showcase what it represents, which means we have a half for our standard formula for a triangle, and then half of our base is AD over here, which is good for us considering we want AD, multiplied by our perpendicular height 1 over here that we have going from E until it reaches the base over there. And then from here, we're putting it over a half of dB over there, which is also what we want because dB is over here, which means that this is the base over here. But then what's kind of strange is that our perpendicular height isn't DE here, it isn't BE either, but considering that this perpendicular height from E all the way up until AD is on the same straight line as BD, we can therefore say that this perpendicular height is the same here for triangle DBE. It just means that we can rearrange the straight line, so that it is fitting inside triangle DBE over there, which means that we have multiplied by perpendicular height H1 over there, which is a good thing for us because what we want is to cancel a bunch of things out, which we can clearly see with us being able to cancel the half over here and the half over there and the perpendicular height H1 and the perpendicular height H1, which leaves us with AD over DB. And that was our statement, and our reason is because they have the same heights, because they are sharing a common side, which means the perpendicular height for triangle ADE over here is the same perpendicular height for triangle DBE over there. A bit weird, but it's just something we're going to have to learn, because now that we've done that with two of the triangles, we're going to do that again for triangle ADE over here, but this time over triangle DCE over there, which means we've taken this top triangle ADE twice, and the first time we took it over this diagonal triangle DBE over here, and then this time around, same top triangle ADE over there, over this other bottom diagonal triangle DEC over there, which means we can just go ahead and write this as area of triangle of ADE, as we said, over the area of triangle EDC, which means that the setup is very much the same as the setup over here. We're going to expand our formula over there, saying half AE this time, multiplied by perpendicular height H2, because AE is our base here. Perpendicular height H2 is connected from D all the way up to the base over there, over a half again, multiplied by EC this time, from here, over perpendicular height H2. Just because they're sharing a same side here, which means that the perpendicular height on this triangle would be the same perpendicular height as ECD over here, which means just like the previous one, we can go ahead, cancel our halves, cancel our perpendicular heights, and we're left with AE over EC, because same reason, we have same heights. But now, because we have this statement over here and we have this statement over here, there's just one more step in the chain, because the area of this triangle DCE and the area of this triangle BED is exactly the same, which means that EDC over here and area of DBE is the same because they have the same perpendicular height here as well. Okay, imagine this was also perfectly straight. So that means we have to write this. So we have to write but area of triangle ADE equals area of triangle ADE. This isn't what we just stated, but we do know this is true because ADE is the same triangle. So this area over here and this area over here are exactly the same. And then like we were talking about, and area of triangle EDC equals area of triangle DBE over there. Because these triangles here have the same base DE and then the same perpendicular height like that. So we just have to go ahead and write same base and same height. And therefore we have area of triangle ADE over area of triangle DBE equals area of triangle ADE over area of triangle ECD. And because this one is the same as this one, it's like we're saying that they're both over 1. They're both over the same base, so we can just drop them. Same thing here with the area of triangle ADE over area of ADE, which means that is the same, which means all that's remaining is just this AE over EC, which is AE over EC, equals this, which is AD over DB, and this is exactly the proof that we have over here. So there's no reason here, we're just saying that because they are the same, therefore they cancel, therefore everything here, as we've proven, cancels out, and these guys are the same, so it's like they're exactly the same as 1, therefore this ratio will equal this ratio, and we can just go ahead and write that down, that therefore AD, just writing it in the same order as we have here, over DB equals AE over EC. Okay, and that's everything we have to do to earn 5 marks over here. So what we have is 10.2 over here. It says in the diagram below, D is the center of a circle. Okay, so that's important for us, which means we'll have a radii over here and a radii over here, as well as a radii over here. AB and AE are tangents, so we got AB and AE over here. So AB and AE are tangents to the circle at B and E respectively. The diameter BG over here is produced and meets tangent AE at C. So both of these guys have just been produced on a straight line and they reach at point C. It says DC equals CG, as they've given us here. We have DG and GC are equal. F is a point on AC such that DF is parallel to AB. Okay, so parallel also important. Cool. So then 10.2.1 says find with reasons the ratio of AC, so AC here, over FC over there. Okay, so in order to find a ratio and us having parallel lines over here, AB and FD over there, the most common way is to do some sort of prop theorem, which means that if we can get a ratio on this side of BD and DC, and we know we have these parallel lines here of FD and AB, it means we can get the ratio of AC to FC over there. Okay, which means we're just going to have to start with the information they've given, and the very important information has to do with stuff like radii and tangents. And if we're going to work on this side, we're going to work with the pink lines, B to G, because that is our diameter, which means that DG equals X and BD equals X as well, because these are radii, they are the same length. But then GC is also X because they've told us that DG equals GC. Okay, which means right now we're going to write all the rules. We have the proportion of BD to DC relative to our parallel lines AB and FD over there, which means what we can write is DB equals DG, so DB equals DG equals X because radii. And then we can say DG equals GC equals X given, which means over here for D to C, we have 2X, and here from D to B, we just have an X over there, which means in triangle ABC, so triangle ABC over there, we've been given that DF is parallel to BA, and therefore, using prop theorem, we can take the corresponding side. So we're going to start with the form that we want it in. So we're going to write AC over FC equals, so it's AC over FC equals BC. So we're going to trace all the way from B all the way up to C over DC. And what we can see, as we mentioned, is that B to C is X plus X plus X. So we have 3X over there, and then DC is X plus X, so we have 2X over there, which means our X's will cancel, and that leaves us with 3 over 2. And we can either write line parallel to one side of triangle, because what we're seeing is a line parallel to one side of the triangle, or we can write prop theorem with the parallel lines. I find that one a lot easier to remember, so I'm going to go ahead and use that one. So we have prop theorem, because we had one side in proportion and one pair of parallel lines, prop theorem, and then we're just writing DF is parallel to BA. Cool. From there, 10.2.2, they say prove giving reasons that triangle ABC, so ABC, this big triangle we were working in, is similar, 3 lines going up, to triangle DEC over there. So we're in the yellow triangle, and we're in the orange triangle over there as well. So I'm just going to go ahead and write the 2 triangles that we're working in again, because it makes it a lot easier for us to orient ourselves. So we're going to say in triangle ABC and triangle DEC, because we haven't yet proven similarity, we're going to look at a couple of angles. Okay, and the best way to go through this is a checklist, because right now they've put it in an arrangement with the corresponding angles and the corresponding sides, which means angle A over here will equal angle D over there. Angle B over here will equal angle E over here. Then angle C over here equals angle C over there. So it's usually best to try and start with the angle that has the same letter. So in this scenario, we have ABC over here and then DEC over there. And if we're tracing it, ABC over here is that angle, and DEC over here is that angle over there, which means they have a common angle, and that's always a nice rule to look for. So we have angle C equals angle C because common angle. And then from there, we just have to prove one more angle, because the third angle will always be interior angles of a triangle. So we just need to find which angle we're going to work with, which means we've started with C. Let's check out E and B over here and see what we can do. So DEC, what do we have here, is an angle like that. And ABC is an angle like this, okay? And right now we have a lot of colors in our triangle, but something to keep in mind is that we've used the diameter or the radii already. We can potentially use that again, but what's very important is always looking for any places where a tangent meets a radius, for example. Because in this scenario, we have this tangent here, AB, and it's meeting this radius here, BD, which means that this guy will be 90 because tan perp rad. So what we can say is angle ABD equals 90 degrees because tan perp rad. So ABD 90 degrees because tan perp rad. And then if we're trying to prove that B equals E1 and we know that they have to be the same, we have to see why E1 is 90 degrees as well. Because E1 is 90 degrees for the exact same reason, because we also have a tangent here, AE, and it is also meeting our red line here, our radii, DE, which means that E1 also equals 90 degrees, also because of tan perp rad. And therefore, angle ABD on angle B there equals E1 equals 90. And this is just proven because of those two reasons we just wrote. So we have a common angle, B is 90, E1 is 90, and therefore D3 over here equals A over there. The third angle because of interior angles of a triangle, which means we can just go ahead and write that. D3 equals angle A because int angles of triangle. And that means that we have three angles that are exactly the same, and therefore we have proven similarity. Therefore, triangle ABC is similar to triangle DEC. So they're not exactly the same, but the angles are the same and their sides are in proportion. And this is because of A. Great. And that would earn us 3 marks over there. And then 10.2.3 says prove that DE squared equals AE times EC over 3. Okay, and this is a 5-mark question, and it is following from a proving similarity question. So usually once we've proven similarity, it's best to rewrite that so we can see our corresponding sides in proportion and start to rearrange things so that we can slot them into here. Which means that we've proven that triangle ABC is similar to triangle DEC, which means we can start to look at the sides that are in proportion. So just like angle A equals angle D, B equals E, and C equals C, this is also in a specific arrangement so we can figure out which sides are in proportion. Because AB over DE is in proportion. So AB over DE equals BC over EC equals AC over DC. AC over DC. And it kind of looks like 2 eyebrows over there and a smiley face. So this is how we take the corresponding sides in proportion. And our reason for this is just similarity, because we've proven similarity and therefore we know that these sides are in proportion. So we just rewrite this over here. And then what we have to do is try and figure out which of these 2 equations have the most overlap with this equation over here. So we can figure out which 2 to take. Because right now we need a DE, we need 2 of them because we have a DE squared. I see a DE over here, so we're going to deal with this guy. And then there's also an AE and an EC. An AE I do not see anywhere, but an EC I see over here in this one, which means we can take this guy as well. So we're going to leave AC over DC. There isn't any overlap with the sides that we want and the sides over here, which means we can just go ahead and write AB over DE equals BC over EC. From there, the easiest way I've found is to move it into the same orientation as this. By that, we have a DE at the bottom, so try and move it to the top. So we're going to move the DE to the top by cross multiplying over there. We have this guy here. We're then going to move our EC to the top as well, because EC is at the top here and we currently have it at the bottom. Okay, so we're going to have AB over here multiplied by EC. And then this time, I'm just going to move the BC down to the bottom here, because what is going to happen is that BC would be multiplying by DE over here, but I'm just going to move it down to the bottom so that DE is by itself and BC is here where the 3 currently is. Okay, because what we're going to have to do is swap some things out, because DE is exactly where we want it and so is EC. Okay, these guys are happy. We just need another DE over here, and the only way we can get a DE over here is in terms of our BC, because 3 times DE will equal BC, so we can leave a 3 at the bottom and multiply our DE up top. We'll break that down just now. And then we'll also have to see how we can relate AB to AE over here and just swap them out, and hopefully they are the same for some reason. Okay, which means let's look at BC first and see how we can relate it to DE so we can get a DE squared. So as we can see, BC over here is this long line, which is x plus x plus x, and that's 3x, okay? If we're looking at DE over here, it's also a red line, and it also equals x over there, because it is a radii, just like this radii and this radii over there, which means all we have to do is write that BC equals 3DE, because we can see here that BC is x plus x plus x, and DE equals x over there, and therefore 3 times x, 3 times DE will equal BC, which means we can just go ahead and substitute that in so long. So it means we have AB multiplied by EC over 3DE. So we've replaced BC over there, and that equals DE. This is great for us because what we can see is that the 3 is over here now, and that is what we want. And then we can just cross multiply DE up to join DE over here. And then we can have DE squared, which means we have DE squared. We have AB multiplied by EC over 3, which means we have DE squared. We have the 3 over here. We have EC. We just need to swap out AB and make it AE. We just have to see why that is true. And looking at AB and AE over here, they are both tangents to the circle from the same point, which means AB will equal AE because they are both tans from same point. So we can just go ahead and write that. AB equals AE because tans from same point. And therefore we can go ahead and substitute that in. Where AB used to live, we can now write AE, and we have AE multiplied by EC over 3 equals DE squared. And that is exactly what we have here. DE squared equals AE multiplied by EC over 3. And this would earn us 5 marks. And then from there, last question, 10.2.4 says, find the ratio of area of triangle FDC over there. So ratio of triangle FDC over here over the ratio of the triangle ABC over there. Okay. Which means we're just going to go ahead and rewrite this formula. This is quite a common question I've seen in quite a few papers. So if we have area of triangle FDC over area of triangle ABC, we just need to see which area of triangle formula we're going to work with. Because in the proof in the previous video, we saw that we were using half base times perpendicular height. But in this one, what's very common is to use our trig and triangles formula so we can cancel out a common angle, okay? Because they're both sharing a common angle here, C, which means we're going to use that one so that they can cancel out. So if we're going to look at area of triangle FDC, we have half, and then we're going to leave space for which two sides we're working in, because we know that we want sine of C because it is the common angle for both, which means that if we're going to use this angle here, we have to use the sides on either side of that angle. And in triangle FDC here, that means that we're using FC and DC, which means that we already have a ratio from 10.2.1 earlier, and the ratio we had was 3:2 for AC to FC, which means that this FC here was 2, AF was 1, and the whole A to C was adding up to 3, which means we're going to take FC first. We'll sub in the values just now, multiplied by DC over there, because these are the two sides, FC and DC, that are on either side of sine C over there. We're then going to do the same thing for area of triangle ABC. So ABC over here, we have a half. We're going to multiply it by sine C, the common angle, so we can cancel some things. And same thing here is that our angle is here. So we're going to take both sides on either side of that angle, and it's going to be AC multiplied by BC over there. So we're going to say half AC multiplied by BC multiplied by sine C. There aren't any reasons for this one, we're just proving it because we've already done the working earlier to get the proportions of the sides, which means we can go ahead, cancel our halves, just like we did in the previous proof, cancel our common angle, our sine C over there, and then substitute the values into FC, DC, AC, and BC. So FC's value is 2 over here, as we could see, based on DC also equaling 2, and we have proven prop theorem in triangle BCA over there, which means FC is 2 multiplied by DC, which is 2 or 2x. Either way is fine because our x's are going to cancel, over AC. AC over here is 1 plus 2, so we have 3, and then same thing here. BC is 1, 2, 3 x's, so we have 3 over there, which means we have 2 times 2 at the top, which gives us 4, and 3 times 3 at the bottom, which gives us 9, and we have 4 over 9 as our final answer. Because here we've just found the ratio of the areas of triangle FDC and triangle ABC. Cool, and that just earned us 3 marks over there, 19 marks for this last question, and 150 marks for this whole paper. Great job, guys. Let me know if there are any questions in the comments below, and then I will see you in the next video.